All right, we can go ahead and get started. I think all our presentations this morning are online, so we'll get to hear a bunch about urban model work that's happening, and also we'll start the FATES sessions of talks. One change to the schedule is Cesar wasn't able to join us, and so either in that time, and I don't know, Rachel, I don't know if you're online, but she's not, okay. We might have, when Rachel does get on, we might see if Rachel can take Cesar's spot, and then Sean has some work that he's been doing that could be, I think, valuable to share, especially in the context of FATES. So he's going to present a little bit this morning too. At lunch today, Sam Levis is leading a discussion. Do you want to, you can just, I think the mics are on, you can say something from there.
Yeah, so this is part of a monthly meeting that happens at NCAR CGD specifically on workplace culture. It happened, I was supposed to give this or facilitate this discussion on workplace well-being, and it happened to line up with this meeting. And so this is today at noon in the Chapman room, which is on the way to the cafeteria if you take the stairs up, not down.
Is that at noon?
Pardon?
Is it in the Damon room?
Oh,
I think it's, well, I don't know. I thought it was Chapman.
The calendar invite says lunch is in the Damon room on the chat behind you.
Right, it's in the Damon room. Thanks. Okay. Thanks, Elizabeth.
Is that a good enough description?
And so if folks do want to go, you can go to the cafeteria, or if you brought your lunch, go ahead and grab your lunch and then just head up to the Damon. Great.
Probably a good idea to have someone go check the Chapman room because they counter. That's good.
Okay. Yeah, I'll hang out there and send you throw it away. Great. Otherwise, we've got dinner tonight scheduled at 6:30 at Avanti. It's a little more space and a larger table. Okay, great. So at Avanti, I think they're expecting us at 6:30. I think if we get there a little early, it's not going to be the end of the world. So if we finish here and you want to head down there, that's fine. At least last year, they had a few tables for us reserved upstairs, and they just had like little things on the table saying reserved. And so we'll just, I'm assuming it'll be something like that, but they haven't really confirmed. Anyway, so sometime this evening we can gather at Avanti for folks who want to have dinner. And I don't know if anyone else has thoughts or comments from the day yesterday or any other announcements they want to share. Cool. Calvin, is our folks online that are ready to present? Like Sam, do you want to?
So we have 4 question mark 5. Hard to count. Got 5 people presenting in this first morning session. Everybody's remote, so we don't have to deal with the lapel mic. First up is Qiyang Xia, presenting about urban climate dynamics. Can you go ahead and share your screen?
Yeah, I'm here.
Yep, we can hear you.
So, yes, everything is okay?
Good.
Yeah, okay. Hello, everyone. Sorry. Wait a minute. Yeah, hello, everyone. I'm Jiang, and I'm a PhD student from the University of Manchester. And anyway, thanks for having me, and I'm really honored to be here and excited to share our work with you today. So as the title suggests, this project aims to develop an AI model that integrates physical information and attempts to predict urban climates. Yeah, so first, I believe many of you have heard of some cutting-edge AI models in climate science, like GraphicCast developed by Google, PangoVisual developed by Huawei, and other advanced models published in conferences or journals. This fully AI-driven weather or climate model are making waves in weather forecasting and climate simulation. They help us push the boundaries of how AI can support weather and climate research. But besides these general climate AI models, maybe it's difficult to develop one that is specific to the urban climate. Since we know the urban climate has its own unique patterns, urban regions are data scarce in climate model training sets. And the AI model often performs worse due to the systematic underrepresentation in the training data. So of course, there are some challenges to develop urban climate AI model. And I think the major one is that the learning process is often inefficient when including urban surface information. So if you train a model before with urban surface data, it could perform worse than the one without such information. And it could be more obvious if you want to do some transfer learning, like developing a model using one city's surface information and applying it to other cities. So yeah, there must be reasons for this. From my side, it could be that the urban surface features are often complex and heterogeneous. So how could the AI model process its data efficiently and correctly if the model doesn't have any specific domain knowledges? So let's first see how general climate AI model to do this. Take the Fengwu model, for example. Fengwu is developed by Shanghai AI Lab and is a powerful weather and subseason AI model. But like many others, it only uses geopotential, basically terrain height data to represent the environment. So this model considers very little surface information in the learning process. So why? Maybe it's a thing for them to lower the model performance if they include more surface information. Because current AI models are what we call black boxes. They are absolutely amazing at spotting patterns in data, but they don't really get the physics behind it all. And this surface data, including urban surface features, are static, which could place burdens or introduce bias to AI models. Without domain knowledge or specific design, this model couldn't use this constant feature efficiently in their nonlinear architecture. So the key idea to solve these challenges is to embed physical and domain knowledge into the deep learning architecture. We focus on the single layer urban canyon scheme adopted in the community land model urban. You can see the urban is one of the land units within the grid cell in the CLM. So in our understanding, we think of the urban climate process in two main stages. The first is the urban surface and atmosphere interactions, where the atmospheric forcing is modulated by the urban surface. Then during this process, there are radiatively interactions between urban surfaces, and the surface energy balance will be achieved. So inspired by this, we decide to incorporate the domain knowledge induction to guide the learning process of AI model. And finally, we hope our model user-former can mimic and represent this physical process. So in the following, I will introduce the model architecture. But before we get into the model architecture in detail, here is the mapping table that links our model components to their physical and domain-specific counterparts. This table outlines the inputs and outputs for each module, illustrating how data flows through a pipeline. So I got some example for the architecture. So the first block in the model is try to represent urban surface and atmosphere interactions. This block contains two key designs. The first is a distinct embeddings. Instead of just mashing all data together, the model smartly separates it into two streams. So by doing this data can retain their unique characteristics, and the model can know where data is coming from. After that, in order to help the model figure out exactly how these two things influence each other, we use a powerful tool called cross-attention. So this cross-attention can be imagined as a member of one group having conversations with a member in other group. So in our urban climate context, the forcing will start conversation by sending a query or question and finding the most important surface information according to the surface answers. So for example, after the conversation, the radiation in the forcing maybe will mainly focus on the urban surface albedo and the surface emissivity. And the wind maybe will mainly focus on the surface morphology. Then the second block is try to represent the surface fluxes interaction in the urban canyon. Like we said, the cross-attention is a process where members of two groups having cross-group conversation. And here we use self-attention to let the data iteratively have conversation within a group to represent the surface fluxes interaction. So because these fluxes need to interact with each other to achieve the balance. So what's next? Let's look at the decoder and see how it uses physical parameters to make its predictions. Since we are interested in three variables in this work, like the urban 2-meter air temperature, specific humidity, and the urban dew point temperature. So most models would try to predict them like there are three separate homework problems. But our model is firmer knows that in the real world, things are all connected, right? These three variables can be constrained through a couple of empirical equations, like the Maglass-Turner's formula. So to use such information efficiently, we add the physical interdependency and another inductive bias, and model such interdependency as an emergent property in the model architecture. And the easiest way to think about it is that when the decoder is trying to predict the temperature, it must consider the message from other two predictions, that is the specific humidity and dew point temperature. So by doing this, we hope it can employ a soft physical constraint approach. So now let's look at how the model performs. I'll skip over the training details, but just briefly. So we train our model using simulation data from community land model urban with data from 2020 to 2045. And we tested on data from 2015 to 2054. As you can see from the results, our model constantly outperforms other baseline across three variables. Because our results are presented as green boxes. Then we use the dataset from 2017 to 2074 to evaluate the model generalizations. In this part, we use probability distribution plots to visualize how will the model performs on this out of distribution datasets. The results are quite promising. Our model stays very close to the ground truth, especially for urban air temperature and specific humidity. So last, I end my talk by discussing about the potential of AI models to move from simulation to the real world. So many AI climate models, including ours, are built and tested on simulation data. But the real question is, the real world application often come with limited observations. So does this whole physical guide things actually work better in the real world? We use a fine-tuning approach to adapt our model to the real-world test. And the fine-tuning approach is about adjusting one developed AI model to perform other tasks. Like a model trained for recognizing cats, adjusted to recognize dogs. Specifically, in our context, we use observational data from the Urban Plumber project to fine-tune our model and then compare its performance with the CMU in estimating latent and sensible heat fluxes. The results were impressive. Even with scarce observational data, our model can be successfully adapted to the real-world setting and outperform CMU in estimating the heat fluxes. So this shows strong potential for future application. So we can combine the simulation with the real world. So by the way, this work has been accepted to the Euros IPS and Machine Learning Conference. And here we want to highlight that this is the first work focused on the urban climate and introduce the community land mode urban to the mainstream machine learning communities. And your work will come to review this work and run this model. And so the takeaway here is pretty clear. So by building our real world knowledge, like the laws of physics and the urban climate knowledge, directly into an AI architecture, we can create models that aren't just more accurate, but are also more robust and reliable. And we want to highlight that this kind of physical guide design presents a transferable concept for broader Earth system size. So this is my presentation. Thank you all.
Thank you. It seems like we have 4 minutes for questions. Anything in the chat? Lydia.
Yeah, thanks. This is a really interesting talk. It's a unique application of training on model output and then fine-tuning on observational data. That's a really interesting direction. Wondering if you fine-tuned on every individual plumber urban site separately, or did you use them all together?
Last question, we only use the UK King's College data sets, not all of them.
All of them. So you end up with one fine-tuned model at the end. Okay, thanks. That's interesting.
Yeah, so I'm trying to think how this would get used in a broader context. Is this like a tool that we could eventually like package up and put out with CSM or CLM for people who want to take this, or do you have a vision for how this could get used more broadly?
Sorry, I don't get your question.
I'm just trying to think about how, what is the ultimate goal of creating this model, right? This ML model. Is it something that could be distributed along with CLM?
Oh, you mean just put the model in the CLM?
Well, no, maybe as a tool along with CLM, not embedded in the model, but as a separate tool that essentially provides value-added information on urban climates.
Yeah. It can be imagined as an emulator for the CLMU.
Right.
Okay, if there's nothing else, we'll move on. Thank you. Next is Junjie Yu, who's also talking about urban modeling, specifically with HVAC control. Are you there? Oh. Yes, you are there.
They're on the same.
You can go ahead and share your presentation.
Okay. You all can see my screen now, yeah?
Not yet.
Sorry. Okay. And very happy to share some progress of my research on reinforcement learning for the HVAC control. And this framework, by combining reinforcement learning algorithms with a CTSM model, and is trying to use the dynamic controls to combining the dynamic controls with the physics model of CTSM. But before going deep into reinforcement learning, I would like to introduce something about urbanization. And this picture shows a typical land surface of the urban areas, and its geometry is a typical urban canyon. And this is very different from the rural areas. And this has been changed a lot of the land surface processes. For example, the radiations and also the turbulence. And we will have lots of the anthropogenic heat emissions from the urban areas. And we can see there will be a lot of the heat flux components in the urban canopy layer, including the radiation, sensible heat, anthropogenic heat, latent heat, and also the storage heat. All these heat flux are collectively affect the local urban climate. For example, it releases the urban heat island effect, which means the urban will host more heat than the surrounding areas. And the anthropogenic heat is one of the most affected by humans, including the building heat, transportation heat, and also the human biological heat. And the most important one among the anthropogenic heat will be the building heat. And among the building heat, there will be 40% of the 40% of the building heat will generated from the heating, ventilation, and air conditioning systems. So which means the heat from HVAC systems will be very important for the urban climate. And with the climate change and global warming, there will be challenge for the designs of HVAC systems. And this picture shows a typical Europe cities and with different warming scenario and emission scenario. And it will largely change the cooling and heating systems of the cities. And for example, in these cities will be shifted from the heating to matrix building energy systems from heating to the cooling. So which means we need a dynamic HVAC control system to fight against such challenges. And we found the reinforcement learning algorithm is very suitable for the dynamic controls, such as the HVAC control. And here is examples to explain what is reinforcement learning algorithms. So imagine we are trying to play a game, and we will try a lot of the try and errors to interact with the game. And for example, when we play the Super Mario's, when we touch the mushroom, we will dive and then get over it. And then if we avoid this mushroom, we will alive but got 0 points. And until the times we learn how to kill the mushroom and get the points, and then we will learn how to play the game. For example, if we see the mushrooms, we jump to kill the mushroom and then get a higher scores. So in the framework of reinforcement learning, this corresponding to the state actions and also the reward. So this is the whole framework of reinforcement algorithms, which means the environment will give the state and reward to instruct the agent to get the corresponding actions. We found the RL will be efficiencies and also scalable solutions for the HVAC control without additional infrastructures installations. And the frameworks for the RL of HVAC controls will be including these two parts. One part is recruit air agent, which is corresponding to the Super Mario's, and then interacted with the building environment, and then the building environment will give the current state and the reward to the agent, and then the agent will give the corresponding actions, and this will be a loop, making the HVAC control decision making be a sequential process. However, we have been noted if we change the HVAC control system, there will be effect to the local urban climate, and then the local urban climate also feedback to HVAC control systems. But in traditional way to do the reinforcement HVAC controls is the one-way simulations, which means only the local environment will affect the building HVAC systems, but they did not have the interactions. So if we did not conclude the two-way interactions between the cooling and heating systems or with the local urban climates, there will be about 40% of the underestimation of the cooling and 10% of the overestimation of heating. And also there will be effects on the outdoor environment. So we must include these two-way interactions. For modeling the two-way interactions and also the building urban climate and building energies, we would like to use the committed land model urban. So the committed land model urban is a component of the CTSM, which is very suitable for this task. It can help us to modeling the radiation, turbulence, building energy, and hydrology among the urban surface. And also it has the capacities to modeling the cooling and heating systems. And for the framework of reinforcement learning used in this study is that we create a region to consider the current and futures to get the maximum reward from the environment. And then we embed the agent to the committed land model urban to see how they will affect the local urban climate, and then modeling how the building energy use and the HVAC system will be changed. The training framework of this study is that because we find the CRMU was writing in Fortran, but most of the algorithms of reinforcement learning is developed in the Fortran. So we developed a surrogate model using the Pythons for the building energy environment. And this environment only included one weight. And after we change the reinforcement algorithm, we embedded it into the Fortran-based CRMU, and then to investigate the two-way interactions. The agent objectives of this framework will be trying to use less cost to maintain an indoor thermal conference. And here we set up a case studies in UK London, and then we modeling the heat pump retrofits and also using the RL to do the heating controls. And the heating systems of the heat pump is something like that. And then these systems will generate the waste heat from the heat pumps and also will be put into the urban canyon. And then the agent will receive the states like the heating set point, indoor air temperatures, local urban air temperatures, and also the electricity price, and then the time embedding to generate the heating set points which as the actions. And the first conclusions of this study is that we train the IR agents, and then the IR agent, it can balance the thermal conference and also the energy cost. But for the first panel, we can see if we have a higher budget for the heating, we will have a greater thermal conference. But we can see the green one is the reinforcement learning algorithm strategies, and they will have a higher cost effectiveness comparing to the static heating control baselines. The H means the H, and then 24 means we set the heating set point to the static value of 24 Celsius degrees, and we find there will be about 6% in our improvement in the cost effectiveness. And we also investigated how the two-way interactions between heating system and outdoor thermal environments. And we firstly investigated how these interactions will affect the outdoor. And in this table, we can see the two-way interactions will make outdoor environment more cooler and wetter. And in this picture, we can see the most affected time will be the early morning. And compared with the baseline RL algorithms, we will have a less environmental footprint introduced by the two-way interactions. But the general conclusion is if we can use less energy for the heating, we will have less environmental footprint introduced by such interactions. So which means if we can improve the efficiencies of the heating controls, for example, using the R algorithm, we can have a less environmental footprint by these interactions. And for the final one is we investigated how these interactions will affect the cost and the thermal concerns. And first, we can see there will be cost increments due to these interactions, and also the thermal concerns decreased by introduced by these interactions. But compared with different strategies, we find the cost of the difference of cost in reinforcement algorithms is more affected by such interactions. But for the thermal convert, it's so different. So which means if we have these dynamic control systems, we will have a higher penalties on the cost. So which means we must concern about the tool interaction by before doing the implementations of such strategies. So for the final conclusion is that in this study, we use the reinforcement learning for the heating control systems, and then we account for the two-way interactions. Our main conclusion is the RL can generate a higher cost effectiveness strategies and also avoid some extreme cost times. But for the two-way interactions, it will increases the cost and also decreases the indoor thermal concerns and the outdoor air temperatures. And for the last steps of this study, we will use some regional simulations to simulate the whole city rather than a local areas. Thank you.
Thank you. We've got 3 minutes for questions. Dave?
Do you think this has potential to, are you, I guess, talking with any energy companies or anyone, any potential stakeholders who would be interested in this sort of information? I guess this is still research oriented, but you can imagine this could be, if you can show a strong cost improvement across many regions, situations, it could be useful information.
Okay. Yeah, this is a very good comment, and I think the building energy sectors will very interesting on these studies, and we are trying to use we are trying to introduce the submodel of CTSM like urban a community land model urban to broader users, including the building energy and also other urban planning sectors. They may be benefits from this model.
Thanks. So following up on that, I think you showed that it would actually, if we bring that external temperature into the optimization of the system, that it ends up increasing the costs.
Yes, because in this study I am modeling the effects of the heat pump. Heat pump is trying to extract the heat from the outdoor to indoor. So if we use more heat pumps for the heating, and there will be more heat transferred from the outdoor to indoor. So which means the outdoor environment will be cooler, and then after the outdoor will be more cooler, the efficiencies of the heat pumps will decrease, and then affect the cost. But this will be a loop of this feedback environment mechanism, and I think it's very hard to trying to explain that.
Thanks. Yeah.
All right. Thank you. We're at 9:45 or 35, so we'll move on to Yuan Sun, who's also presenting on urban in CLM. That's convenient. You're all there together. All right, you can go ahead and share your screen.
Okay. Mm.
Share the screen first.
There's no notes.
Okay.
Hello everyone, I'm Yuan. It's my honor to present our recent work in the winter group meeting. Today I will talk about the WolfCMU coupling techniques, and we compare it with the.
Share again.
Oh, sorry.
Share. Okay.
And thanks my supervisors and co-authors. The CMU is the urban model of CTSM. We know that urban climate is scale dependent. So varying different scales, we would find the different urban components. They are like urban surface and the urban block, neighborhood, and cities. So in the CMU, we used to run global simulations at the large scale. So we have for land only or coupled simulations. While for the urban model development work or the model evaluation work, we also use the low single point simulations at the local scale. So the single point is only driven by the data atmosphere. While for the meso scale or regional scale, CTSM and or CMU also play a role. However, we found that at the regional scale, they are only data atmosphere, and the WOLF or the other active atmospheric models are seldomly used. So this study want to couple the WOLF with the CMU and use it at fine resolution. This work is based on the previous coupling development that we noticed that last year, the WolF CTSM has conducted the first simulations at a grid spacing of 10 kilometers. And the coupler is named the LILAC. The source data is already available in the CTSM's GitHub repository. We found that the LILAC is a separate coupler that bridging between the WolF and the CTSM. And before that, the CLM4 has a numerical weather prediction version. So this code is already embedded within the WolF. So this is the code differences between the CMU5 and the previous version. Our contributions is that we found WolF CTSM at 10 kilometers is still too coarse for urban climate simulations. For urban modeling, we may pursue higher resolution, for example, 1 kilometer. So the nested domains are required. We will introduce how to use the nested domains and which is a workflow that is suitable for the WolF CMU. The first step is we need to prepare the WolF input. The input includes the meteorological data, and we also have the surface data. They are varying from different domains. And then we will run a wolf simulation first. This wolf simulation is served as downscaling. For example, we have to download the meteorological data from ERA5. However, ERA5 is 0.25 degree. It's 25 kilometer. So we need the downscale, the dynamical downscaling. And then we need to prepare the CTSM input. First is the mesh is generated by the wolf. So we need to map the atmosphere mesh to the land mesh. And this land mesh is structured. So we have to unstructure it. And then the unstructured mesh can be used for the mix of data ESM tool to generate the surface data for CTSM. And then the downscaled meteorological data is used for wolf. And then the LILAC will couple the CTSM here with the wolf. The simulations will come from two sources. These two models will produce their corresponding outputs. So here we would like to advocate for the wolf CMU from several aspects. The first is that we enable the atmosphere-land two-way interactions so that we can capture the urban signals in the atmosphere or the broad climate system. And the second thing is the wolf is an active tool that we can downscale it for the meteorological data. Therefore, urban climate simulations, we can reduce the limitations from the availability and the quality of the meteorological data. And we also noticed that there are recent advances in the wolf CMU, like we have explicit air conditioning adoption, and we have transient urban, and we have USURF. This is 1 kilometer data. This can also be used along with the wolf CMU. So we want to use it maybe in the future to see their performance. And another thing is we find that the wolf is a family with different urban models. So maybe we can join it and see some like ensemble approach to see the differences between different urban models. But we know that CTSM is rather complicated. And when we coupled it to the wolf, we want it to be simpler. So there are some configurations to reduce the complexity. It's more like a function for the numerical weather prediction. So here we listed two configurations. One is the standard and another is the fast. For the wolf CMU, we will adopt the fast configuration, and it simplified the number of plant functional types to a single type. And we also collapse the urban from three default classes, the town building district, the high density and medium density, to a single urban class. And we also have the other settings that let the machine to run faster. Here we recommend to change the default number of dominant land units from the true to false. This will retain the subgrid land cover heterogeneity. So we still have different land cover types. Here we will introduce a case study in Greater Manchester. So the innermost domain, the fourth domain, is the Greater Manchester, and before that we have to run a three-nested domain for wolf downscaling. So we run 1 year for the year 2022. and we compared the WOF CMU to WOF's default urban scheme. The innermost domain is 1.2 kilometer spatial resolution. I will quickly introduce the results because for the urban, there are very different urban physics and initial conditions. So definitely the difference between these two simulations are large. We evaluate the model performance at 3 sites. Here is the map shows that Head ISD is a station at the Manchester Airport. And we also have Manchester Air Quality Super Site and the Whitworth Station. They are closer to the city center. And the performance are evaluated by different metrics. And the grid field in dark showed the better performance. We could find that generally 2 sites, 2 urban sites, the MAQS and the Whitworth Station showed better performance for WOF CMU, while for the Head ISD, we find the WOF default urban scheme has better performance. We think that this come from different aspects. One is the different representation of urban, and the model physics is also different. While for the Head ISD, the Manchester airport is less densely built, so it's more like a rural site rather than an urban site. So when we run the simulations, the WOF CMU might overestimate the thermal environment, and the WOF default represents this site as a rural site, so it's more. It's cooler, so it may contribute to its better performance. And the summary is that we demonstrate that CMU has the capability to run high resolution urban climate simulations through the WOF coupling. And since we have this capability, we have a lot of things to do maybe in the future that we can evaluate the model performance at different urban sites. And we may run ensemble simulations to see the model sensitivity to atmospheric conditions from different surface data. And we may also apply the new development into the WOF CMU. And another thing we want to mention is that can we imagine if the MPass can be coupled with the CTSM? Because we know that this WOF is stopped development and the NCAR is moving to the MPass. So some similarity is that for the next generation land atmosphere coupling, the mix of data ESM maybe can adapt to the mesh that the MPass adopt, which is a Voronoi mesh. So maybe in the future, we can explore the potential of this. Thanks. Sorry, I forgot to mention that this project is publicated through a preprint. So please feel free to explore more. Thank you.
Thanks very much. We have time for one question. It seems like there was one in the chat.
Do you want me to read it?
Yeah, please.
Yesterday asked, how about the model performance at 1 kilometer? I'm wondering whether we need to adjust the urban structure and model physics in CLMU at 1 kilometer spatial resolution.
Yeah, at 1 kilometer, we still use the default urban setting, so it only has vertical transport of the heat and the water variables. It do not have for horizontal transport that may be suitable for 100 kilometers. that's why we do not explore it to local scale. For local scale, CCMU is not suitable. So we think a local scale maybe is 1 kilometer is the maximum or the finest.
Can I ask one follow-up to that question? And it sounds like in your WARF simulations, you only used one building class. And I'm wondering for these 1 kilometer simulations, if you had some heterogeneity, if you'd be better able to capture the kind of more rural setting where the airport was located.
Do you mean that for the airport site, the WARF default scheme has only one class?
Yeah, like you use the low building density, or I can't remember scale and urban model, but you use the lower building density as opposed to the high density building district. That would give you better results for that grid point.
Sure. Because here we only keep everything the default setting. So the airport only has a medium density urban class derived from the surface data. So that's why maybe it would be overestimated. So we might replacing it using the other surface data, more precise urban parameters. The WARF CMU maybe also can show good performance.
All right, thanks very much.
Yeah, I know we have to move on, but let me just note that there's this MPAS question about MPAS and CTSM. We can actually run with the MPAS dynamical core in the CSM framework already, and MPAS physics is being pulled in through this CCPP activity. So before too long, and I don't want to give a date, but there will be the capability to run MPAS within the CSM framework. And as Eric said, we can create the grids already. So.
Okay, thanks for letting me know.
All right, thanks. Now we're going to shift from cities to forests, which makes sense because as we all know and say, what is a forest? But that's right, a city of trees. First up is going to be Cesar Dionisio Jimenez Rodriguez. Okay.
Rachel, are you online?
Yeah, I'm online.
Are you willing to jump in here so we can kind of keep with the...
Sure. Yeah, I'm happy to jump in.
Thanks.
Okay. Okay, are you all able to see my screen?
Sort of. It's a blurry browser window at the moment.
Oh.
Slightly sharper browser window.
How about now?
Yeah, we're seeing the slides not in a presentation mode, but yeah.
Interesting. Okay, I will try and go to maybe just full screen.
Sure, that works.
Okay, that works. Great. So we'll just stick with that. Okay. So switching gears, I'm going to be talking about some work looking at carbon allocation to reproduction and its leverage on Fates predictions of forest structure and demography. So this is preliminary work using the Fates tree recruitment scheme at Barrow, Colorado Island. And I think a couple of yesterday's talks motivated this work really well. So we know we need to be able to predict forest responses and feedbacks to global change. And we would like Fates to be able to simulate where and what types of plant functional types are able to regenerate in a given set of environmental conditions. And so what this figure is showing is the large proportion of forested area in the American tropics that is young secondary forest. So the tropics particularly, we know we need to be able to represent regeneration, but that has not really been something that's gotten a lot of attention relative to growth and mortality in these vegetation demographic models. So a little bit about Fates. Fates is a cohort-based vegetation demographic model. So this is something that runs coupled with a host land model. And it's a little bit of a compromise between a big leaf representation and an individual-based representation of vegetation. So within each grid cell, Fates represents multiple patches that have similar size structure. So you can think of each lollipop tree here as not representing an individual tree, but a cohort that belongs to a particular plant functional type and size class. Then energy and water fluxes are calculated for each cohort and patch and aggregated to the grid cell. And each patch shares a disturbance history. So within each patch, we represent processes that give rise to emergent vegetation dynamics, growth, mortality, and recruitment over time. And for those of you unfamiliar with the terminology, recruitment just is referring to those trees that are entering the smallest size class that the model tracks. So you may wonder why we would expect reproductive processes to influence forest structure and demography. And one reason is that the first step in reproduction, the carbon allocated to flowers, fruits, and seeds, exhibits a really well-supported trade-off with carbon allocation to growth. So if we start with a budget of NPP, once storage and maintenance costs are paid, we have some remaining available energy, and we have good evidence that some fraction of that is allocated to reproduction and the remainder to growth. And so you can imagine that if you're underestimating the carbon allocated to reproduction, you're going to be overestimating carbon allocated to growth. And at the individual scale, we have really good evidence that this trade-off changes as plants grow. This is something sometimes referred to as an RA schedule. And I think intuitively, this makes a lot of sense. We don't expect very small trees to be producing flowers and fruits. So if you plant an apple tree or a lemon tree, you need to wait until that tree is big enough before you get fruit. So for long-lived trees, we tend to see that they begin allocating to reproduction at about half of their maximum size or age. So we have some information about when trees start allocating to reproduction, but this max allocation is a little bit uncertain, although some empirical work suggests that by the end of life, trees are allocating 100% of their available energy to reproduction. So we can represent this trade-off in Fates. So I'm going to walk sort of quickly through this diagram, but we're going to focus on this first step that I have highlighted. So in Fate's default regeneration scheme, we start out with carbon for growth and reproduction. Some fraction of that is allocated to reproduction and enters a seed bank. And then there are parameters that determine seed decay and seed germination. And germinated seed mass becomes carbon available to be converted into new recruits, or the smallest size stem size class that the model tracks. So the environmental insensitivity here is a big limitation because we know these processes are very sensitive to environmental conditions. But I want to focus on two simplifications that we make related to this allocation to reproduction. So the first is that the default model assumes that reproductive allocation is static across size classes. So small tree, large tree, doesn't matter. 10% of your available energy for reproduction and the remainder to growth. And the second assumption is that it's more of an assumption about the parameter values. We assume that 10% of carbon for growth and reproduction is allocated to reproduction for all tree PFTs. And part of the reason for this assumption is that we haven't really had data that lets us think otherwise. So I do want to highlight some new work. This is actually the first chapter of my dissertation. And in this study, what we were able to do was validate a proxy for ecosystem scale reproductive allocation that's constructed from pretty widely available leaf and reproductive litter fall observations. And what we found is that there's an approximately 60% increase in ecosystem scale reproductive allocation from boreal to tropical forests, and that reproductive allocation at the ecosystem scale increases with forest age. So a little bit surprisingly, the magnitude of that age effect was comparable to the magnitude of climate effects. But this, I think, makes sense when you think about a forest as a collection of trees that each have an reproductive allocation schedule. And so in an older forest, you have a larger proportion of reproductively mature trees allocating more of their available energy to reproduction. So this data set is available, and the litter fall proxy that we use, I hope, can be sort of a useful, practical ecosystem scale benchmark for modelers, whether or not you're using Fates. But returning to fates, we can now represent size-dependent reproductive allocation and environmentally sensitive recruitment using the fates tree recruitment scheme. But this is relatively untested. So to go through this very quickly, and then we will again focus on reproductive allocation. Again, we start out with carbon that's available for growth or reproduction, and now there's a size-dependent fraction of that carbon that's allocated to reproduction. In the phase tree recruitment scheme, we now have a step where we differentiate between seed and non-seed reproductive biomass. So seed versus the biomass that we assume is for flowers, fruits, pine cones, other reproductive structures. And the seed mass enters a seed bank. And then there are light and moisture sensitive functions that determine the fraction of the seed bank moving to the seedling pool, the fraction of that seedling pool dying, and the fraction of that seedling pool that becomes new recruits. So this was developed a couple of years ago and mostly tested offline using inputs from a different host vegetation demographic model. It was brought into the main branch of fates, but not really used, I think, until this point. So I think I'm the first one kind of playing with this model. And because we have all of these light and moisture sensitive functions, there are a lot of new parameters. So the objectives of this project are sort of first to identify sensitivity of model predictions to TRS parameters, then develop working parameterizations for a light demanding and a shade tolerant plant functional type at Barrow, Colorado Island. So these are really commonly represented ecological strategies in the tropics, which are important for successional dynamics. And then the third objective was to assess the leverage of regeneration strategies on structure, demography, and relative abundance. And again, we have some expectation that our demography will be sensitive to regeneration because of this trade-off between carbon for reproduction and carbon for growth. So I developed a 1,400 member ensemble parameter perturbation experiment. We used Latin hypercube sampling to sample parameter ranges for 25 TRS parameters and 19 other parameters that are associated with these ecological strategies represented by our light demanding and shade tolerant plant functional types. We run these simulations as single point simulations at Barrow, Colorado Island in Panama using recycled observed meteorology for 300 years from bare ground. And I'm just going to talk about, these are very preliminary results. So I'm going to focus on the ecosystem scale rather than the PFT specific results that we're seeing. Okay, so here's just the spread of the ensemble predictions of above ground biomass. And you can see this gray bar is showing the observed range at Barrow, Colorado Island in the background. And if we look at how sensitive demographic outcomes are to TRS parameters, what we find is that this max reproductive allocation parameter explains above 40% of the variation in our ensemble AGB, and it is the TRS parameter with the strongest leverage on all demographic rates. So here I'm showing sensitivity of above ground biomass, mortality, growth, and recruitment to all of the TRS parameters, which you don't need to be able to read. I did sort of expect some of our other TRS parameters to influence predictions of recruitment, but really this max RA parameter was very dominant. And so if we look specifically at this relationship between max RA and above ground biomass, what we can see is that max RA has a negative linear relationship with above ground biomass. And so for every approximately 0.1 increase in that parameter value, we see about a kilogram carbon per meter squared decrease in above ground biomass. And it sort of makes sense that this parameter has a lot of leverage because we varied the range really widely. And so if you'll remember, in default Fates regeneration mode, we assume a max RA of 0.1 which is at the the lowest end of this spectrum. And then theoretically, we know that that parameter value could be as high as 1, meaning 100% of available carbon is allocated to reproduction. Okay. And then if we look at size structure, we can see that the differences in above ground biomass are driven by accumulation of AGB in the largest size class. So these plots show the average above ground biomass in each size class. So each bar on the x-axis represents a different stem diameter class. And on the leftmost panel, you can see I've just bin simulations by their parameter value for maximum RA. So when max RA is low, that means we have a lot of carbon allocated to growth, very little allocated to reproduction. Many trees grow into this largest size class and a lot of biomass accumulates there. Whereas at the other end of the spectrum, when we look at simulations with high max RA, we have all of their energy going to reproduction, very little to growth, and as a consequence, very low biomass accumulating in the largest size class. So the next steps in this project are to compare ensemble member predictions with our observed benchmarks and retain best performing parameter sets. And one way we're going to be able to do that is by using the ecosystem scale benchmark for reproductive allocation that I talked about earlier. So here on the x-axis, you can see I'm plotting max RA parameter values, and on the y-axis, the predicted ensemble scale, the predicted ecosystem scale RA. And in the background, the gray bar represents the observed ecosystem scale RA at BCI. So we can sort of see here that 0.1, the default value, is a little too low, but anywhere from 0.2, maybe all the way up to 0.8 or 9, we might see reproductive allocation parameters that make sense and allow us to meet this ecosystem scale benchmark. So that's sort of how this benchmark will help us calibrate simulations, but obviously, there's a lot of variation, and I think that's because the rest of this reproductive allocation schedule matters. So you could have a simulation where the max RA parameter is very high, but if, for example, your trees don't start allocating to reproduction until they're very large at the ecosystem scale, that means you have relatively low ecosystem scale RA. So takeaways, reproductive allocation varies over biomes and forest age, and we now have ecosystem scale benchmarks that can be estimated from litter fall. And the second takeaway is that FATE's TRS can mechanistically represent reproductive strategies, and work to parameterize is ongoing. So we can see max RA parameter as a dominant control on above ground biomass and size structure and demographic rates. Getting it right matters for predictions, especially size structure. And I'll leave you with that.
Maybe a few questions for a few minutes for questions dedicated to this talk, and then we can move into general discussion.
Sean has some other stuff to share.
Oh, okay.
She always has some questions here.
Yeah. Audrey.
This is amazing. I guess, I mean, I'm interested if you have any thoughts or plans to do a study in like a really different biome, so like boreal or temperate. You know,
Okay, I've talked.
Do you think it might change your like sensitivity or something?
So one limitation to the TRS right now is that it was developed for tropical ecosystems, so there's no temperature control on recruitment. And I think before we run this in a different biome, that's something that needs to be addressed. But I am interested in running this in a temperate system, like especially if we think about, for example, redwood trees, which have a very distinct regeneration strategy where they allocate very little to reproduction and instead grow very large and live very long. I think that could be really interesting, but I'd be happy to talk more about that if you are interested in.
And then I would love to see, I'd love to see your size class structure. Mm-hmm. Like if you could try to produce like the classic, like J, you know, like, I don't know, shape of like what you would like typically find in like a temperate zone, like old growth is like that J.
Yeah. And I think one sort of direction I see this going is that I think we will need multiple PFTs that have distinct regeneration strategies in order to capture that observed size structure. So I cut this for time, but in the tropics, people have previously tried, you know, to capture observed size structure with just two plant functional types representing like a slow strategy and a fast strategy, like a late successional and an early successional PFT. But what they end up missing is this. Here you can see sort of the discrepancy in the largest size class here. These species that have a lot of shared characteristics with an early or a light demanding PFT, but have a different regeneration strategy. So instead of allocating to reproduction and dying pretty quickly, they grow and live long and allocate very little to reproduction. So with just 2 PFTs, you can't really capture that. And so this is like from a paper a couple of years ago using ED2, where they pretty well capture, early PFT, late PFT size structure, except for this huge fraction of the biomass, which is dominated by these long-lived pioneer species. So I'm thinking that's the direction that this work is going, but we're getting TRS working and figuring out how, the competitive dynamics work with just 2 PFTs first.
Yeah, Rachel, super cool. I guess I was just curious why the parameters that could actually control the RA schedule, like the size at which that S curve happens. Why didn't that show up in your sensitivity analysis?
So I think the reason is just because we varied that max RA parameter so widely. And when you start to look at some other, so I just showed AGB growth, mortality, recruitment. When you start to look at the sensitivity of, for example, AGB in the largest size class, AGB in the smallest size class, growth and growth by size class, growth by PFT, then you do see stronger sensitivity to those other parameters that define the reproductive allocation schedule. Yeah, but just at this sort of top level, I think because I vary that parameter so widely, it really dominates in terms of its leverage.
Thanks.
Very interesting study, and the results are very amazing, I think. So I have a question, kind of like follow up for your current page. So if like the reproduction allocation is increased up to maybe 0.8, 0.9 to some very high values, it seems like it's gonna fundamentally change the life strategy of that PFT or some specific species. So in that case, I feel like in addition to reproduction allocation, some other features or the parameters gonna covariate with reproduction allocation. For example, the turnover rate gonna increase as well. So will that affect the importance of reproduction allocation?
Can you say that last part again? You said something's going to increase as well, but I didn't catch.
Just for example, the turnover rate.
Okay, yeah. So I think that's sort of a question that maybe we can, if I'm understanding you correctly, I think maybe that's something we can answer with faith. So one thing I've wondered is we don't really know if, for example, a reproductive allocation schedule that increases all the way to 0.8 or 0.9 will cause higher mortality, higher canopy mortality rates for PFTs with that schedule. Is that kind of what you're getting at?
I guess my question is the covariance between the reproduction allocation and the other factors.
Oh, okay. So the covariance between reproductive allocation schedule and growth rates, for example, or photosynthetic traits.
Yeah, some other traits, yeah.
Okay, yeah. So we actually do have some, I think 3 or 4 good empirical studies from a couple of different tropical forests that look at traits that explain demographic variation. And so what those are finding is that we have one axis of demographic variation that is explained by sort of these fast and slow strategies. So growing fast, dying fast versus, being shade tolerant and living longer. And then there's a second axis of variation related to this, what they call a stature recruitment trade-off, which is sort of what I'm getting at when I'm talking about these long-lived pioneers. These are plants that share some functional traits with a fast plant strategy, but grow for a long time and live for a long time because they don't allocate very much to reproduction. So we do have some data that we can use to sort of constrain the parameters that are also going to be related to the reproductive allocation schedule, but not defining the reproductive allocation schedule. So yeah, parameters related to growth, for example, and wood density and some other functional traits. We can look at the.
I think at this point, Sean Swinson has some stuff to present. I'll let you take them. Oh, sorry. Yeah, cool.
Yeah, this isn't like a talk. This is just an advertisement for a project that we finished this summer, which was to include spatially distributed parameters in the model. And so, so basically what we did is we tried to take column or grid cell level parameters and enable the ability to make those vary spatially within the model. And so the way it works is you can choose some subset of parameters of the available parameters and add those to a streams file, a separate streams file, which will have the spatial distribution of those parameters, and then you can read those into the model and do those. And then for parameters that you don't want to do that, it'll just revert to the standard global parameters that we have. And then the way that we wrote the code was the code doesn't know, you have to change the code anywhere. The code doesn't know whether or not it's coming from the streams file or the standard parameter location. So that is sort of, yeah, it's agnostic to those kind of things. And right now that's in a, there's a pull request for that, but you can go ahead and if you want to try this out, so for people that are doing, you know, calibration and things like that, you could go ahead and try this out and apply some of these parameters, you know, with regional differences, regional variations. Yeah, you can check that out. Was there any? Wait, there's one other slide. So these are the parameters so far that we included, and some of these are either more applicable to things like hydrology. So, for example, base flow parameters, a couple snow parameters, some of the soil property modifiers, et cetera. And we didn't apply this to like the TFT level parameters because that seemed that was just going to be too unwieldy to have, you know, streams file with global TFT parameters. But I do have a separate branch where I have, and I'll mention this later. I think I gave some slides to Adriana, where we can do some spatial variations in some of the plant functional type parameters, but that's separate from this. So this tends to be just the grid cell and the column level. So yeah. Hang on.
Yeah, someone go ahead, Sam.
Well, this has some similarities. We've discussed this before, but to the spatially distributed crop parameters that we had in a few versions ago. So if you're interested in the audience, if you're interested in working on spatially distributed parameters, there are also options to do that with crops already. We can add one.
This guy question is just where is this? It's not in the main code base yet, right? It's on a branch. And is it planned to be part of the CLM release, or is that? I don't know.
We haven't gotten there. We're trying to get it. It sounds great. Mm-hmm. I think we can probably make it happen. Didn't prioritize it most.
Yeah, this is great. I just wonder if you can share a little bit more technical details of how the spatial distributed parameters were derived, because there's some other ongoing efforts using machine learning to derive this spatial variant parameters. So I just wonder, like, the technical differences.
So this is just the code to do that. You provide the spatially variant parameters. So that, yeah, there's a bunch of people that have been looking at doing calibration, but there hasn't been, you know, a model version that could take that data. So there's no particular set of spatially variant parameters that we've used with this. We just tested with sort of dummy arrays where you make this one twice as big and make this one half as big, and then you look and see, does that show up in the history file? So that's kind of the extent of the testing right now.
So basically, the users are going to provide their own data set, like own variables, and specify what parameters going to be calibrated. And this code will help the users do so.
That's right.
Okay, cool.
Yeah.
Hey, Sean, this looks amazing. The SF, they're scaling factors, are they? That's the idea that you can tune up a region for like specific emergent properties.
Yeah, cool. Yeah, so these are, as opposed to trying to sort of go in and look at like the transfer functions or do the specific values here, you can just modify the standard values, go up 100% or down 50%.
Really cool.
Yeah. Just to be clear, these are just the parameters that you worked on to start, but you could add more, a user could add more, or we might add more through time. Or what's the strategy?
Well, I think these are most of the, I have to go back and look and see. These were most of the parameters, again, at the column sort of grid cell level that we had, that we pulled out. I don't know if anything was excluded from that, but
there must be more than that.
It seems like there would be more than that, but this was like 6 months ago, so I've forgotten. But yeah, so at the very least, this would provide a template for doing that. Yeah. And also as part of this, we pulled out some of the parameters that were nameless options to facilitate this. So kind of moving away from having, quantitative nameless variables and putting all those into like a parameter file.
That's very cool. So have you tested with this? And if yes, did you see any improvement in model performance, especially by capturing like specific spatial pattern?
Yeah, no, I haven't done any testing with this. Andy's not here, but Andy Wood's group's done a lot of calibration focused on like stream flow. But most of that so far has been, for example, focused on like CONUS for North America. And so as people start to expand this to like global, then we'll be able to have, we can have some data. But yeah, we haven't tested that yet.
We have a few minutes to kind of move into broader discussion. So Rachel gave us a nice intro to some of the capabilities that Fates has. I think Sean's talk kind of alludes to some more, fine scale calibration and parameterization work that could be enabled by having this spatially explicit calibration tools in the model. And then all the urban talks, again, point to this kind of increasingly high res capabilities. And I don't know if there's any topics that folks kind of ideas that are bouncing around in your head or discussion topics that we want to have. Or caffeine is needed.
It's sort of not a discussion topic as much as just a demonstration of the value of having a community model. I think that the urban talks made that really clear, right? Built the framework and then they're like doing a ton of value added stuff, bringing in machine learning, AI stuff, coupling and going to ultra high resolution, just all these things. So to me, they were really enjoyed seeing that, I guess.
All right. See, are we coming back at 11? Yes. Yeah, great. Let's go take a break now. Continue the conversation out in the hallway and see you guys later.
We have a series of talks. Next series of talks is on Fates, so that'll be going on. And I'll find speakers at 15 minutes. We'll try to see if I can enforce that or not. But thank you.
Shielding the microphones on the floor.
Okay. Sorry.
Cool. So welcome back to your first in-person talk today. So I'm going to talk about how we can model management activity in phase. So first of all, I want to acknowledge all the collaborators who have contributed to this project. So historical fire regime in California ecosystem are characterized to be frequent, low to moderate severity fire under indigenous stewardship. And the use of fire is to keep canopy open and also reduce wildfire risk by removing both surface and lateral fields. It also promotes post-fire resprouting and tree regeneration. So nowadays, we tend to see a news report on mega fires almost every year, especially in California. So what happened is we started a century-long fire suppression policy starting in the late 19th century in those forest ecosystems. And during this relatively fire-free period, what we see is that there's a significant accumulation in the surface field load as well as increase in the understory vegetation. And we call this dense understory vegetation as lateral fields. So what it does is when we have a surface fire in the system, the fire can easily climb up onto the tree crown and then become crown fires through those lateral fields. So this makes the land management community realize that, okay, by removing fires from those fire-adapted ecosystem cannot actually prevent severe wildfire. Instead, we need to return fire to the landscape, and that requires the use of pressurized fire. A recent study done by Swing et al. Using modeling approach showed that we might face a significant decrease in the number of days that are suitable for conducting pressurized fire across the Western United States. And that poses a question about whether pressurized fire can still be effective as a fuel reduction approach in a warmer and drier future. We're also not clear about the long-term management outcomes, which in part is due to the complex interactions between climate and elevated CO2. So under elevated CO2, so the aperture of plant stomata is smaller compared to that under a lower CO2 concentration. And that prevents water loss, which increases live fuel moisture content, and that indicate a decreased flammability. However, elevated CO2 also can promote growth, which leads to more biomass accumulation, and that increases the landscape flammability. So how elevated CO2 influences the use of pressurized fire, especially under a dry condition, and how that interact with changing climate to affect post-disturbance vegetation recovery is not clear. And all this point to this big picture question. So what drives the long-term management outcomes in the context of changing climate and shifting fire regimes? Where does the uncertainty come from? And process-based model is powerful tools for answering such type of question, and that requires the model to not only accurately represent the vegetation dynamic, but also capture the key ecological process by which management affect ecosystem dynamic. And I'm going to focus on the second part today. The model we're using a phase model, and thanks to Rachel, who already did a great job introducing phase, and I'm going to skip this. So in this project, we aim to develop a mechanistic pressurized fire model and adapt a pre-existing logging module to represent pressurized fire and thinning as fuel management activity in phase, and also test if model can capture the general ecological expectations by which pressurized fire and thinning affect wildfire and vegetation dynamics. So fire in phase is represented by phase speed fire, and the fire occurrence is determined by weather fuel condition as well as ignition source. After we have a successful ignition, the model will predict key fire behavior metrics, including rate of spread, fire duration, fire intensity, flame height. And some of those variables will be input along with some PFT-specific fire resistance traits, such as bark thickness, to determine post-fire vegetation mortality. And in order to represent pressurized fire, we developed a new management fire model called Phase RX. So Phase RX incorporates a burn window concept. So the model compares the site-level climate condition to user-defined weather condition for temperature, relative humidity, and wind speed. So as long as the three weather variables are within the user-defined range, the model will flag a burn window to be present. And after we have a burn window, then the model will check the current patch level fuel load and fire intensity against user-defined range. The reason for checking fuel load is to make sure that we do not have management fire occurring on a patch that has a very low fuel load, which means you don't need to manage that, or have a very high fuel load, which means your control burning might escape into a wildfire that is out of control. And the reason for checking fire intensity is to make sure you can achieve the desired management outcomes, because different management goals might require different fire intensity. And instead of letting the model to determine the proportional land area that will be burned, we actually set up a maximum area, a daily burn area to reflect institutional burning capacity. And the post-fire vegetation responses is determined by phase speed fire. Phase also have a logging module. So plant either will be removed directly during the logging or die due to collateral damage. And that kind of influence the surface fuel load, because except the logged trunk will be transported off-site, all the plant residuals will be left on the site, and that will contribute to the surface fuel load. And in order to better represent mechanical thinning in practice, we further modified the model structure to prioritize removal of small and medium-sized trees, because that's usually what is done, especially if you use logging as like a fuel reduction strategy. So we tested the model across 3 sites in Sierra mixed conifer forest. Those are Blodgett, Staff, Tea Kettle, and those sites distributed along the climate gradient and also vary in their stand condition. So to run the model, we included 4 plant function types: pine, fir, cedar, oak. Those are the dominant plant functional types in mixed conifer forest. And we use parameters from previous work done in California mixed conifer forest. But we further tuned the leaf allometry in order to have the persistence of a dense understory vegetation. And we initialized phase using site-specific inventory data, and by spinning up the model for 20 years in order to reach fuel equilibrium. And after spinning up, we did 4 different modeling experiments. So one of the simulation is a control simulation where we did not apply any management. And one of them where we applied logging only treatment according to site-specific prescription. And the other 2 simulations are where we apply pressurized fire. But the differences between the 2 simulations is how we set up the burn window. So one of the simulations use an inclusive burn window setting. So more than 25% of each month are available for conducting pressurized fire. And the other one use an exclusive burn window setting. Well, the burn window only mainly happen in early spring and late autumn. And the model is forced by Wolf downscale climate data from 1980 to 2020. So first, let's look at how phase can well represent site structure. So what I'm showing here is the site structure for the control simulation with the model data in black, observation in gray. So what we can tell from the figure is that except the underestimated stem density for trees below 30 centimeter at Blodgett Staff, especially at a Staff, phase can well capture stand structure using inventory initialization. But this is the result at the end of the simulation. And we also look at a model simulated fuel load and compare that to observation for the control simulation. So what I'm showing here is a model and observed fuel load grouped by different fuel size class. So the main message here is that the model tend to overestimate fuel load and the higher fuel load in the model is largely due to a much higher fine woody debris, especially due to the large branch. We then, that's no title. So we then look at how treatment influence the site structure by looking at the relative change in stem density by size class. So what I'm showing here on the x-axis is a different size class. On the y-axis is the relative change in the stem density by size class, which is calculated as the differences between the treatment control divided by the control. See, there's something wrong with the animation, but what I was actually trying to show or draw your attention to is at Biogeochemistry first. So if you focus on Biogeochemistry only first, so you can see both data and the model show that show a decrease in the stem density for trees below 50 centimeter following prescribed fire and thinning. And that's pretty much the same story for staph and tea cattle. Especially for thinning, you might tend to see more data model deviation for fire. Sometimes observations show decrease, but the model tend to show a slightly increase. Okay. So we then look at how treatment influence the field load. So if we focus, so what I'm showing here is a relative change in the fine woody debris and also relative change in dead leaf fields. So if we focus on Biogeochemistry first, we can see that both model data shows decrease in the fine woody debris following prescribed fire, but increase in fine woody debris following thinning. So, and for the dead leaf fields, if we focus on staph, we tend to see both data, the model shows significant decrease in the dead leaf fields following prescribed fire. We don't have data to show thinning effects on dead leaf fields across the three sites, but most literature point to increase in the dead leaf fields following thinning, which is also captured by FATES. Lastly, we look at how treatment influence growth. So what I'm showing here is the growth response for the 3 dominant conifer PFD, pine, cedar, fir. On the y-axis, I'm showing the treated to control growth rate multiplier. And the red dashed lines are reference line at 1. So if the multiplier is about 1, that indicates a positive growth response. And if it's below 1, that's a negative growth response. So let's focus on staph here because it's just a little bit easier to see given the scale. So we can see for burning, both data and the model tend to show either slightly negative or slightly positive or sometimes neutral effect. But when you look at thinning, it tends to show more of a positive response, growth response to the treatment. And it's pretty much the same story for at Biogeochemistry and the tea cattle, especially for thinning. But we tend to see more like variation across PFD and across size in the model. So you can see that for pine, it tends to show significant positive growth response to fire at Biogeochemistry and tea cattle, but tend to be neutral, more of a neutral or slightly negative response to fire at a staph. So there's more variation going on for fire effect on growth. So here are the take-home messages. So when the inventory initialization phase can well represent stem structure, but tends to overestimate the field load, and both model and observation show decrease in small and medium-sized trees after treatments. So suggesting prescribed fire and thinning can effectively remove lateral fields. And prescribed fire is more effective in reducing surface fields because we tend to see actually increase in surface fields following thinning. And thinning tends to stimulate growth, but prescribed fire effects on post-treatment growth can vary among PFD and the sites. So we benchmark phase according to established theories to ensure accurate model projections of the long-term management outcomes under global change, which is an ongoing modeling effort. So stay tuned for that. Thank you.
Really good standard to set up a time. So let's make sure everybody can hold that standard. But so one quick question while we change over.
Yes. Did you compare the different soil moistures from the different stimulation scenarios?
We haven't done that yet, but are you trying to see does the treatment influence the soil hydrology?
Yeah, to see if there's like correlation between the what you see with the fuel and different.
Yeah, it's possible. By reducing stem density, you might tend to see a higher soil moisture.
All right. Thanks, everybody. Yeah, so I'm going to continue the FATES discussion so I feel like for the past several versions of the video, I've given like an iterative version of like this exact same talk where I make a little bit of progress each time. And this is going to be another one of those. So, okay, so we have I think there's a key new FATES capability since last summer, which is that we can now do these historical full land use change scenarios. That had been kind of the last key missing piece before we could do big global transient, historical and future scenario simulations, because obviously that being able to do these global land use is necessary for that. So that's sort of like been a practical problem. The other way of looking at this is that FATES offers a lot of potential to ask questions about land use, right? Because FATES, the fundamental reorganization of FATES is to take a disturbance mosaic-based approach rather than a PFT-based approach. It allows you to reflect both the natural and anthropogenic land use and disturbance history, and how these two, how the natural and anthropogenic land use, or excuse me, disturbances interact with each other. And one key thing to just always keep in mind is that that the FATES representation of land use differs from the what I'm calling the classic, because the classic throughout this talk, CLM and ELM relationship of land use, because in the relationship between land use and land covers, right? So land cover is like the PFT fractions, and land use is how primary land, secondary land, pasture, rangeland, et cetera. In the classic approach, there's this pre-processing step where you first take the data set, which comes from the integrated assessment models on as land use, and then you translate that into land cover, i.e. PFT cover, before you actually run the model. Whereas in FATES, at least in the current configuration, using this no-comp configuration, we ingest these two pieces of information. One is we directly ingest the land use itself and force the model with land use. And then in this sort of no-comp configuration in which we prescribe the land cover, that's basically by looking at this, we also ingest a static data set that's land cover conditional on land use. So for each land use class, there's a set of land cover classes. And so with those two pieces of information, you can then cover everything. Of course, at some point in the future, we want to relax at least this constraint on the naturally vegetated land, so that we allow the land cover to be fully prognostic, and on the less anthropogenically managed landscapes, and maybe more guardrailed by human activity on the more intensively managed land use classes. Okay, so what does some of this stuff look like? So here's like an example of a global integral of both the patched land use types and age distributions over time. So the different colors are the different land use categories, and that's basically just reflecting the driver data. The black lines are the areas of each land use category that's driving the model. But then the emergent piece is, for example, the age distribution you get on primary and secondary lands that reflects this disturbance history. So secondary lands has in general a much younger age distribution than primary lands. These things are evolve in time. And so there's you get more out of this than just the information you put into it. But the crucial thing is you get sort of the correct answer in that these things sum to what the driving data says it should be. Okay, so now we have this capability, so we can do things like the trendy experimental protocol. So this summer, both I did this and Kettle did this in the NORI SM group, and contributed the FATES configuration or FATES output to the trendy protocol, which is you do 4 experiments. You do a control, a CO2 fertilization only, CO2 plus climate, and then CO2 plus climate plus land use, and then you can sort of deconvolve the different drivers based on the difference in these two lines. And so, for example, in this configuration, you see a couple of features that are a little bit interesting and worth diving into. So, for example, in the control, it's not just a straight line. There's actually this low frequency oscillation that happens, which I think we're still trying to uncover exactly what's going on there, and whether that's like a feature that we feel good about, or something that reflects some underlying dynamics that are non-realistic. But it's there in these simulations. Under the CO2 fertilization, it's got a not super strong CO2 fertilization. It's on one of the weaker models for this particular calibration across the trendy models. The climate forcing then reduces the land sink. And in this particular configuration, land use then causes, for much of the 20th century, the land to be a source and then switch to be a sink in the most recent period. Okay. And I don't want to dwell on a lot of this stuff, but I think the key thing here is that it's not totally crazy. when you could put it amongst the rest of the trendy models. It's, it's doing some things reasonably well. It's doing other things not super well. It's going to, we just need to iterate, calibrate, get this stuff ready. But like out of the box, the first time doing this, I sort of expected it to just be like all red, and it's not all red. It's like, it's not totally crazy. So that's good. Okay. It's just some of these dynamics. So for example, if you look at the zonal mean of this difference between the with and without land use, and to infer like what's the carbon flux due to land use, you see some patterns that kind of what you'd expect to see, which is that land use is mostly a source of carbon coming out of the tropics. You see the kind of indication of this long-term mid-latitude regrowth. It's fairly weak, but it's present. Because of the land abandonment in much of the mid-latitudes and secondary forest regrowth that's happening there. And if you so on the left is the total carbon flux, on the right is just the DDT of the vegetation carbon, showing that it's, the vegetation carbon is largely driving this. Okay, so I just wanted to do investigate some initial structural sensitivities, and what I want to do is to talk about two specific things. One is initial condition sensitivity. So there's two possible ways of spinning up fates with land use. There's something that's the most analogous way to the sort of classic CLM way of doing it is you do this, what I'm calling a late pre-industrial steady state spin up. So basically, we define the land use areas. We pick a point in time. This point I'm spinning up for year 1700. So we pick the land use patterns for that year. And then we have to back calculate a set of secondary land harvest rates that would give you the age distribution with respect to anthropogenic disturbance that you would get on a millennium timescale transient run. That includes things like both, whatever harvest may have happened prior to 1700 that the secondary land is still recovering from, as well as any shifting cultivation that would cause the abandoned land and the shifting cultivation to have a young secondary land age distribution. So that's one way of doing it. So it's basically constant land use and then constant harvest rates that gives you a secondary land age distribution that's younger than primary land. The other way of doing it is that you start off with a no land use spin up, and then you do all the land use that would give you a 1700 areas all at once, which at the start of your transient run, which then creates this excursion, which then you need to let sort of propagate away. And so I wanted to look at what are the implements of that. Another thing is there's a bunch of sort of uncertainty around how to deal with some of these land use types. So one thing that we wanted to investigate is how aggressively to clear land during transitions to rangeland. So you can either, you can clear all the rangeland during transitions, or you can not clear it and just allow things to change slightly because of grazing fluxes on rangeland. And I wanted to explore those two end members. And so these show these different sensitivities. So the solid lines both have no clearing of rangeland, where the dashed lines both have clear all vegetation when you convert to rangeland. And then the difference between the black lines is that this is from this constant 1700 spin up. So it's most analogous to the way of spinning up the classic model, whereas the green lines are they deforest much of the planet on the first day of 1700, and then allow things to recover from that. And so what you see here is that both of these two structural sensitivities we're exploring, they have like long-term implications. In particular, that you might expect the spin-up sensitivity to have kind of disappeared by 100 years, maybe 150 years into simulation. That turns out not to be the case. You see that there are these long-term persisting differences in land use, particularly under the case where you don't have clearing of rangeland. And I think that's because that decision sort of then allows some of these spin-up differences to then propagate longer in time. And then the other key sensitivity here that we're looking at is this rangeland clearing. So that's the difference between the sort of upper pair of lines and lower pair of lines later in the simulation. And so this is a really strong source, difference in the overall sort of top-down behavior of the global carbon cycle. Is just like this one decision about what do you do about rangeland? Whereas if you don't clear rangeland, you get kind of the expected sink to source transition, source to sink transition during the mid 20th century that is kind of consistent with observations. In this simulation, if we clear out all the vegetation during rangeland conversion, then the land actually never becomes a sink. It stays a source throughout the recent history, which is not really consistent with our understanding of the global carbon cycle. And then, so that's on the left is the global NBP, and on the right you see again these big differences in the global GPP integrals because of these decisions about land use. And just to dive a little bit more into what's causing some of these differences. So both the differences in the initial conditions and the differences in this land use conversion. The big difference that you see during the initial conditions, I mean, under the sort of coarse-weighted debris and litter carbon, you see this big pulse initially because you've deforested a big chunk of the planet, but then that kind of decays away. On the soil carbon side, you also see an initial pulse of that litter propagating the soil carbon. Interestingly, that never really decays away. Those lines stay divergent from each other, at present day. So it's reflecting this like long-term multi-centuries persistence of some of these spin-up protocol effects, which is probably real, right? I mean, actions that people have taken over millennia, are present in the world we live in, and so this just gets to show some of these long-term legacies of how you treat land use during spin-up. Whereas these differences between how you treat rangeland clearing show up much more strongly in, say, the vegetation carbon, where again you have much less vegetation carbon if you clear out the vegetation in the conversion to rangeland than not. And likewise, and also you see, in the more recent period of the simulation in the soil and litter carbon as well. And then just looking at some of these like benchmarking to say, okay, well, of these, at least of this rangeland clearing, you ought to be able to maybe, say what the difference is. So here's showing on the top row is no rangeland clearing. The middle row is with rangeland clearing, and the bottom are observations. On the left is biomass, and on the right is GPP. And what you see is that in the absence of rangeland clearing, if you look at South America, you see that like the Amazon just kind of continues on all the way over to the Atlantic forest region, right? There's nothing kind of missing in the Cerrado region. Whereas with rangeland clearing, you see a much more realistic absence of vegetation or biomass in the Cerrado region that's much more consistent with the observations. And likewise, you see a similar pattern in the GPP. So the simulation with more aggressive clearing during rangeland, it shows much better agreement with these sort of remote sensing observations. So that then creates kind of like a bit of at least in this particular calibration, we've got a bit of a conundrum, right? So with aggressive rangeland clearing, we're better satisfying the bottom-up constraint. But if we go back this slide or back a couple slides here to this top-down constraint of the global NBP, it's less consistent with the fact that we kind of know that the land is at least a weak sink. And so, yeah. So just summary, this is just like a first attempt to try and play with some of these things and understand some of these global, historical transients, but we now have this capability and we can iterate from. The spin-up protocol leaves this long legacy. The recommendation that I would give is to use this constant land use method for spin-up. It's more analogous to what everybody's always been doing with CLM, and it avoids these kind of long transients associated with a no land use spin-up. But like it's also not fully realistic, right? In a sense, you could think of these both as end members of how you might actually represent land, the antecedent land use history effects on the current carbon cycle. There's high uncertainty related to how to handle some of these details of land use conversion. So I just focused on one around rangeland conversion, where the complete clearing leads to better agreement with the bottom-up remote sensing benchmarks, but it then also degrades the top-down benchmark. So I think there's further recalibration, and in particular, making the CO2 liberalization sink stronger in the model would then allow us to be more consistent with both of these things. So there's a lot of work to do. There's, happy to share this output, and I'm excited for this to be a much more widely used capability. So I'll stop.
Question from Alea. Nice talk. I'm curious what to do with carbon pools and creating rangelands. You just deallocate it or respire it?
There's parameters that the conversion, some fraction of it gets burnt off and some fraction of it goes into the pools.
Quick question. Is there a question in the room? Well,
seems like, and this is probably a calibration question, but
it seems like you have high forest biomass to begin with, both at high latitudes and in tropics. And then I'm curious, when you cleared a rangeland, is that I see seaport grasses and CLM are giant pain. I'm guessing that's what your rangeland is becoming.
Yeah.
How does GPP and how does product? It was kind of
Yeah, you can see a little bit of that here. I mean, there's lower productivity when you clear the rangeland in like the Sahara region than there is forests. So it's not like the seaport grass is like it's like super productive. There's nothing really obviously pathological about it. She's to say it's not there.
Next up is Adriana, which if I understand it right, is going to be both part presentation, part discussion.
Yeah. Yeah.
Adriana's my other really pathological.
Oh, yeah. We'll see. Okay, thanks. Yeah. Okay, so this is supposed to be mostly discussion. So let's see if I can not take up the entire time talking. But yeah, so in case you hadn't heard, FATES was going to be we're going to be having, for CLM, FATES is going to be our new default vegetation model. So the plan is for the next release, so CLM 7, we'll be using FATES. That's the plan. We've decided. Okay. So, all right. So I just want to talk about, so, I mean, everybody covered a lot of great, but I just want to really high level, like what is FATES? Why are you moving to FATES? And then how for CLM? So, right. So if we think about like what vegetation does, like it has these processes, interactions across all these different spatial and temporal scales, cell all the way up to landscape. So CLM BGC does the top row and then the canopy really, really well. It does a good job. And then we're missing those last two circles, but that's why we want FATES. And so, this is really old news for ecologists, but we know that forests are a mosaic of patches. So we have like a gap, dying tree, and young trees. And the forest dynamics are then the average of the responses of many such gaps. And so FATES is a model that tries to represent those dynamic processes. And so it's a cohort-specific model, so we're grouping cohorts of trees of similar size and PFT. It still does the 30-minute or however many, depending on your host land model, photosynthesis and fluxes, but then it has daily growth and allocation, so we get dynamic vegetation, which is great. And why do we care about that? Well, forest height, structure, age, and competition all feed back to climate. So if we want to get the carbon cycle right and we want to get climate feedbacks right, we think we really need to do this. So how's it going? For CLM FATES, we've been working on calibration. So this is a look at what I've been doing with global SP calibration. We're doing a pretty good job at constraining parameters that are important in SP mode to get biophysical fluxes correctly. And then, so we got global SP calibration. Other people are doing, so Nori SM folks and Charlie are doing global no-comp calibration. And then I'm also, along with a lot of other people, doing single point calibration. And here for CLM FATES, that's been in Boreal, Canada, Western Colorado, and then US neon sites. And then we just now, as of this morning or last night, we have no comp spin up going. So this is our first with Charlie's land use. We're doing global, no comp, carbon only with land use spin up. So this is year 1850 FATES biomass and LAI. Globally, I don't know, this is looking at the green is FATES, so that's only got up to actually this morning it's 1960, but I couldn't get that figure made in time. But so the GPP compared to CLM BGC run and a CLM FATES run in green. So yeah, the GPP is a lot lower. I don't know, the CO2 is, I don't know, we'll see. So the LAI is actually higher in 1850, but then it's declining. And then there's NPP, which is actually higher than CLM BGC, and then the biomass is also higher, but it's falling. Anyway, so more to come with that, but that's just where we are. The big thing is that here's looking at performance metrics. So the green is CLM FATES. I ran this on an NE16 grid. The purple is BGC F19, which is sort of similar. And then the blue is an NE30 grid, so that should be way slower. And luckily it is way slower than the NE16 FATES, but FATES is about, we kind of already knew this, but CLM FATES is about 3 times slower than CLM BGC. So that's something that I think we're going to try to work on. So our near-term goals is to have this V0 CLM FATES by CLM 6 release. That's for SP and no comp mode. We want to have CLM nutrient coupling by October. Some single point calibration. Oh yeah, sorry, I was supposed to have people. Okay, here are the people that are involved in that. Sam, Will, and Ryan are working on the nutrient coupling. Lydia and I have been doing a lot of work with the calibration workflow. We probably then need to recalibrate with nitrogen coupling. Sean just showed me some really cool way that we can add more Fates PFTs in fixed biogeography mode without making a whole new surface data set. So that will be really helpful. Other project ideas that we have that I just sort of wrote down. So Fates is slow. Can we speed it up? Ryan just now has this new way of doing, I'll just say all of this, almost all of the extra runtime is in the canopy fluxes because we have to loop over all the patches and all the cohorts to do that photosynthesis. And so Ryan has come up with a way to do that in parallel, and it speeds it up. So that will be really great. Coupling with Gordon's multi-layer canopy model. So how can we utilize the variability of Fates to improve land atmosphere coupling? So there's a handful of folks that I just didn't ask them and put their face up there. And then, okay, so then we have Fates crops and Fates plant hydraulic stress would be really great to have we have Fates hydro, which is a really complicated Fates hydraulic version. And then the other way that you can run Fates is with the BTRAN sort of soil moisture stress. It would be nice to have something in between. And we don't have anyone working on those, so it'd be really great. So what you might have noticed, it's a lot of the same faces and then a lot of question marks. So basically what I'm saying is help. And so what I would like to talk about now is who wants to do, what other science do we want to do with CLM Fates, and what things do we want to focus on in the next years to come, because we're still going to be here working. So, okay. Thank you. And then, Sean, if he wants to talk about his thing, I have those slides up there, but maybe we'll just kick it off. Yeah, thank you.
I think this is really great. We're going to have 22 minutes or even longer for a discussion. We haven't really had in-depth discussions about Fates and its coupling with CLM. We hear a lot of talk about it, but there are a lot of issues and things to work on and a lot of science to do. So let's see if we can get a discussion going. Does anybody want to lead off with anything?
We're going to start by turning on the chat just a second.
Yeah,
pretty heavy.
Yeah, there's a question in the chat that was answered, which is do CLM Fates if CLM Fates not sacred? And I'm right.
Okay. Yeah, there you go.
Yeah, now we have NORIA-SM. So this is, I think one of it is going to be a management. We have to have a management question of, now we've got 3 major groups, 3 major land versions and 3 major Fates versions that are kind of going on that we need to maybe get better at managing. But because ELM and CLM folks meet regularly, but the NORIA-SM Matt Lee does come to our meetings, but I think we need to get better at doing that part. But that's more of a logistical question than anything. Yeah.
I think crops would be really great. I know we had the early conversations several years ago about trying to integrate crops into Fates. I just don't think that there's any dedicated time or person to work on that is part of the problem. But as Sam answered in his question yesterday from Rosie, I think parts of the existing code could go in, but I'm also, we started working on agro-IBIS development, and that basically dropped. I think the code is still there. Bill Sachs was working very closely on that. Our collaborator at UIUC, and again, there's just not funding or dedicated resources for it.
Access, right?
Absent.
Yeah, okay. I thought you said agro-IBIS.
I might have. It is agro-IBIS right now. It's APSIV is the update. Yeah, so I probably misspoke, but thank you. Yeah. So
that's the problem with all of these things is that person problem. Funding.
I think the crop model provides a really interesting example of the challenges of moving forward because it's built around the existing BGC code. It uses the existing leaf photosynthesis code in CLM. So if you want to run crops, you have to run the old BGC code. And how do we deal with that within the limited sort of the resources?
Just the one piece that we are at least starting to work on a little bit is So one thing you can't do with fates right now is because all the patches sit on the same column, you couldn't have irrigated patches and non-irrigated patches. But what Greg is working on right now is building a patch to column correspondence, which once that's working, then one of the things that would be enabled by that is you could then do irrigated and or fertilized patches.
I think that's actually going to be the biggest impact on fluxes is accounting for irrigation and fertilization management. The individual crop types are important in their own way, and the planting dates are important, but I think the management aspect of it is probably the biggest thing to capture in terms of getting fluxes right if we want to focus on this as an earth system model or land component to our system. So that's what I would advocate for is.
So that's one of the reasons why we're working on it.
Sort of continuing along this line, it's something I'm going to talk about this afternoon. I think it's the duplication of code across models is really the big thing we're going to have to address moving forward. Leaf photosynthesis is just a perfect example of that. I'm not sure what the path is to do that, how we resolve that, but that's sort of the crux of the crop model problem. It's like, well, we got all these different photosynthesis codes. How do we move that into, how do we find a common photosynthesis code that works for all different applications?
Yeah, I would agree. And I guess one thing I want to add, I know Rosie has her hand raised, but one thing that I want to add is this, what we saw earlier today by Rachel with a reproductive allocation could be very useful in a crop scheme as well, because, that's like one of the big things that crops do is they reproduce. So maybe we could leverage that in some capacity.
Yeah, very quickly. Rosie, yeah.
Hey everyone. Thanks Adriana. This is super exciting. And what was I going to say? Yeah, on crops. I keep sort of hearing in the crop literature this kind of thread that like existing crop models are not sort of representing crop damage events from heat and drought stress and things. And I feel like, fates has all this kind of mortality and damage functions as integral to its kind of function. And I feel like that could be actually kind of beneficial for crop simulation in the end. So I think I'm going to pivot a little bit to trying to include that in some project applications in the next EU round. So we'll see how that goes. I think that was all I wanted to say.
That sounds great, Rosie. I do think that that's a big thing that's missing in CLM. And I think we can leverage the strengths of fates for crop modeling purposes. And so maybe we need to just rethink how we want to move forward with agriculture.
Yeah, I think I agree with Gordon. Like the last thing I want to do is like duplicate code that doesn't need to get duplicated. But if we can design how we want to manage the crops and where that code needs to go, and then I think we can do that effectively without like rewriting something that we don't need to rewrite, right? And use leverage what faith brings to the table.
Yeah, because the way forward right now, which is running BGC code and fates, you're already talking about fates being 3 times as expensive, and then you add the BGC on top of that, and it's just going to be prohibitive.
Yeah, and right. I mean, maybe that's a gap, like a thing that we can do, and if we can figure. I mean, I don't know which is easier to figure out how to run crop BGC at the same time as fates, or just redo main crops and fates. I don't know, but yeah, I think.
Yeah. So it's probably time to really start thinking about it though, because there are a lot of developments with CLM crop that that are great new.
Yeah, we don't want to leave those on the table, right? Yeah.
So this is Queen from University of Virginia, and I want to advocate for the partnership with university to develop fates, especially like I have heard of like a lot of parameters for initialization and also for parameter tuning, which seems to can only be improved with more specific data or localized data. And considering how complex the face model can be, and this cannot be done by a single agency and would be facilitated by multiple agencies with different funding proposals. And one question I will have is for the NCAR for how to broadcast such kind of like face. Is there any training for the model for model learning? Or I heard there's a long learning curve to initialize this work. And if we have a more clear code for running and for calibration and all kinds of spin up, and it would be facilitated using it for other agencies like outside of NCAR.
Yeah, so I want to totally co-sign what you said, that we totally rely on our university collaborators here, and they're invaluable. And then in terms of the fates, we're going to have a tutorial in November, which I will just say, yeah, we'll have definitely have a fates component. And we are, as face developers and users, we're constantly trying to make it more user friendly. I think that the learning curve has been brought much less steep as maybe I just naive now because I understand it more. So I don't know, but I hope that it's an easier use now. But yeah, so and that's a large part in what we do here is that we try to help other users and users learn more user friendly. Yeah.
I'm just going to second that. I think it's really clear that there's a lot of work that needs to be done to continue CLM and advancing it and the coupling with FACE and other science we want to do. We don't have the resources here at NCAR to do everything. We rely heavily on DOE, with FACE. And that's working, but we need even more people involved with it. So I'm looking at this particular moment in time as a really big opportunity for the university to say, take ownership of the model and say, here's how we want to contribute to the model and further the model. And that's what I think the opportunity is, and maybe not the opportunity, the need is right now. You have a question too.
Yeah, that's actually following up on this nice discussion here. So we have a DOE project to look at the topics, and we're using the face model here. So my students have also spending a year to learn the model and to calibrate the parameters.
Yeah.
So I think Ryan is probably there. We also have some help from Ryan, and also the amazing face team in Orange Berkeley Lab. So the question is, when we calibrate the parameters, we have to take a step-by-step approach. We have to start from a static mode, just to worry about the parameters that are related to physiology, make sure it's physiology right. And then the next step is to worry about demography and also allometric equations. And now, after a year, we finally get into the allometric equation side. And there are many different options of the equations and different parameters. So that gives us a lot of headache. So I just wonder how we can, we don't want to reinvent the wheel, and so we want to learn from what has already been tried, so that we can make the efficiency a little bit higher. So that's why I want to bring this up to see how we can collaborate better with NCAR and also Orange Berkeley Lab.
Yeah, I agree with you. And I think the idea is that we have all sort of our three big groups of the NORISM, ELM, DOE, and NCAR have been working on is to get this at least a baseline version of FACE, no comp mode that just kind of works generally out of the box. And then, maybe you need to tune it a little bit specifically for yours if you have a very specific study site. But, and then also we could all separately working on these ways of calibrating the model. And I do think that we want to have a tutorial or a workshop or some kind of thing that we all come together and have this is how you want to you have a single site or a region in FACE. Here's how you can calibrate it. And here's what we recommend as the workflow. And I agree with you, Leela. I think FACE has a lot of different options. And I think you can see that as a blessing and an interesting way of exploring different, experiments and hypotheses, but it also can be a curse in that, you don't know which one's which, right, to use. And I think the hope is that we have this V0 FACE. It's this is the best, this is what we recommend starting with, that will at least get you something reasonable out of the box. And then you can go from there to fine tune it for your purposes.
Yeah, so specifically the calibration process, right now I've been doing manual tuning, of course, to fit our like specific sites. But I wonder, given all the nice talk yesterday about automated calibration and more advanced approaches, just wonder if on your side, what are the next steps?
That's what I've been doing is with the emulator, with Paint. So that's what I've been doing. Basically, this following Lydia's footsteps and Daniel and Katie's footsteps and trying to automate the calibration of Paints. And I actually don't know what I think. Rosie has also been using emulators as well. Maybe Rosie can. Sorry.
Point first, and which is just there's a lot of collaboration, international collaboration, on fades, and I think the challenge is how do we coordinate this across all the different flavors and all the different fades that are being used, the models it's being coupled to, and how do we then bring the universities into this? How do everybody play in this environment so we sort of know where it's headed? And so anyway, but there is a lot of that already in place. I hope there'll be even more of that, as university people come in, and then we'll have to figure out what's the right way of sort of managing all this stuff across NOR-ESM, CLM, CESM, ELM, E3SM, all these different models that are using PAIDs. But there's structure in place to already do that. That's, I think, what I want to get across. So,
I totally agree. And I think just to people who have already indicated, just main thing, a fundamental thing we need to know is who's doing something or interested in doing something. That's like order one, and then we can check. Without knowing, we can't manage it at all. Yeah. So order one is we have to know. So contact Will, Adriana, Rosie, Charlie, whoever really, and then we can figure it out. The second is just, you just said this thing about calibration. We're totally aware that we need to have tools, and we're building tools. And I think a goal for sure is that we're going to try to build some tools that the community can use. Right now, we're trying to share them across internally to make them robust. But I think the next step is to make them community outlook. And that's when we're going to get to that exactly. We haven't really said, but that's definitely the goal. Like we hear that.
I don't want to hog the question. Are we other questions? Because I have this very specific calibration. Yes. Yeah, we do have a question online. Go ahead.
Hi, everyone. Thank you so much. I have developed a workflow in CLM that optimizes crop yield for each county. So I was wondering if FATES or any other CLM versions allow us to use county level parameters to run at a single run.
Sean's tools.
Yeah, Sean. Yeah, I mean that's actually a great segue. I was going to say if Sean wants to come down here and briefly talk about ordaining. I don't know. Yeah.
Okay. Okay. Earlier, I advertised the spatially distributed parameters for sort of the non-PFT level parameters. And then I've also been interested in this idea of trying to get not just spatial variability, but like just more diversity in terms of the PFTs in CLM, but without having to just continually increase the size of your surface data file. So right now we have sort of some structural constraints in CLM where for example, if you want to add PFTs, you have to simply just start increasing the size of the surface data file. And then there's sort of hard-coded assumptions about the orders and all these things. So as part of that in CLM, I restructured the surface data file and how you read that in to try to get rid of some of these constraints. And what that does is it allows you to have kind of an arbitrary number of PFTs. You can have 100 PFTs if you want, without having this huge surface data file. And so every location, you could read in some subset of that. And so what that was meant to enable was ideas of, there could be large differences in certain PFT types. So like a deciduous tree, you may have really large differences in the same location. So it's not just the spatial piece, but also just the PFT diversity. So I got that working. And then showed that to people, and people were like, okay, well, that's fine, but that's not, we want to do FATES. So since then, I have worked to try to get that into FATES, and I'm close to that. I had something working a few months ago that I haven't worked on it. When I tried to merge it on Friday, I broke it. So the point being is I almost have that where, for example, you could have you just have a larger diversity of PFTs. I'm sorry, this is specific to either FATES SP or fixed biogeography, not full FATES. But so then you could have, for example, a whole bunch of boreal PFTs in a grid site, one location, and a whole bunch of tropical PFTs. In tropical location, you could do global run all at the same time. So I don't know if that was clear at all. But we're working on doing that kind of thing. Just like a simple example, Adriana gave me some parameters, and I expanded the parameter file. So I have a parameter file with more than the standard, 14 PFTs, and then here I just stuck those in different places, and this was just running one with and one without to sort of show that you could get these spatial differences. But again, I think even more interesting than that would be to have these different PFTs operating in the same grid cell. So again, you could have there's I think I put that on here. So there's all these different kind of science questions that you can't really ask if you have just a single broadly deciduous tree. If you want to look at like the species level variation and look at like what different water use strategies or other kinds of strategies are, then you can't really do that in the current kind of structure. So hopefully this would enable some of those kind of questions. Oh, and sorry, I was just saying, if that's the kind of thing that would be interesting, then you can just contact me and I can let you know when I have this fixed.
Any follow-up question? Yeah, Rosie. Yeah, Rosie.
Hey, Sean, that's cool. I guess I'm sort of interested in the kind of mechanics of that. Like, we have this like map thing in FATES, the sort of, we call it the HLM PFT map. And in there, we can say, in the FATES file, we can like define an arbitrary number of, say, broadleaf evergreen trees, and we can say where you have area, which is broadleaf evergreen trees, split that area into the arbitrary number of broadleaf evergreen trees. But we can't say where they are, right? We can only say like it's like a fixed fraction would go to PFTs 1, 2, and 3 per broadleaf evergreen. So like, what have you done that? Like, what have you done how does this work? This is what I want to know.
It's more on the CLM side where you can specify these things. And so the concept's pretty simple. It's basically, instead of having this implicit ordering where you assume that the PFTs all have the same order, you explicitly pass in an index that tells you what these different things are. And so then at any given grid cell, you don't have to have PFTs 1 through 10, you can have PFT 1 and 5 and 100 and 200. And then at the grid cell next to it, you can have a completely different set of those. And you don't have to sort of pass in information about all 200 of your possible PFTs. So, so it's more just like a structural change that you do there. And then it's just and then I just have to finish a piece of passing that into FATES where you do the same thing. And then ultimately, if you do that, you don't even have to have this, you don't have to have the mapping you're talking about. You don't even have to have a matrix anymore. You can just have a one-to-one. So you can then just have every single one that you want. You don't have to split anything. You just have the size of the model, you have everything. And then that would actually do away with that matrix idea in the mapping.
Well,
that makes sense.
Yeah, my immediate was, we could have, we already have the temperate versus boreal in the surface data set, needle-leaf evergreen, but I was thinking about the tropical, the paleo versus neotropical. Like we could just do that really easily with Sean's thing if we wanted to make a new FATES PFT that varied, but just by allometry and then spatially. We can't do that right now, right, at all, really, without changing the surface data set, but now we can with Sean's stuff. So
maybe one last question, then we'll head to lunch with Peter.
Sean, I was wondering, is there a time, can you have a time varying version of this too? Like, so that you have, well, if you think about like climate's changing, so like your composition might be changing in terms of your species.
I don't
Or
see why not. Yeah, like I said, it's just kind of structural change, and you just have to change this index then, as opposed to these other things.
So really
But
cool.
we could go over the code sometime, and
yeah,
I can show it to you, and you can say yes or no. That kind of thing.
yeah, I just thought like just having that ability would be really, really phenomenal actually, to have transient changes in these, I guess, spatially varying properties.
Yeah, well, I just want to leave you with, just keep thinking about this question. I guess I should say, what science do you want to do with CLM based? And I will say that if you are a science, if you come to us in the next, I don't know, starting now, and you say, I have a cool idea and I need help, and I'm going to do it with CLM BGC, we're going to say, that's awesome, you should do it with dates, and we're going to be happy to help you. So, yeah. Okay, thank you.
That was great.
One thing for lunch, and I think meeting going on over lunch too, that people wanted to talk to work. Lydia, did you have something?
I was going to ask you what your calibration question was offline.
Oh, yeah, well, yeah, okay. You're in on this too.
I'm implicated.
Oh, no.
So cool.
Okay, hi everyone. Let's get started for our afternoon session. So I'm Katie Dagan. If you haven't met me, I'm going to be moderating with Peter Lawrence. And we have 5 great talks on kind of a combination of hydrology, multi-layer model. We're going to talk about some software engineering at the end of the session. So real good mix of things. So to start off, we're going to hear from Naoki Mizukami, who's going to talk about an update on Mizu route in CSM3.
Okay, so I am talking about Mizu route. It's a river model component. It's not the land model component, but I'm talking about I've been working on coupling Mizu route with CSM, so fully coupled ocean too. So I'd like to acknowledge like Eric, Dave, Sean for some occasional discussion, especially Eric for technical support. So CSM3, this is a CSM3 picture. Okay, river model interact with mostly land model, but also important to know is there's ocean. That's a tricky part. And then also, I think CSM3 now, river model coupled with land ice. I think it's trying to send ice melt to river model. So I think that's a new thing. So status of Mizu route at the top, I put in the top. Land only couple, I think it's getting mature, and then I'd like to see people using more and more, and then I'd like to hear my feedback for scientific or also usability stuff. So yes, I'd like to see people using more. The fully coupled mode, I put the construction mark. It's not quite there yet, but I made some progress, so I wanted to update here. So before talking fully coupled runs, I just a kind of advertisement for land model coupling. It's mostly probably interesting hydrologic applications. Yeah, we can get the stream flow estimate for high resolution, and then we can put some to look at the water management stuff. So this is NLDAS domain with a high resolution, like it's called Merit River Network. This is a comp set. We can create case, and then we can run out of box, and then you can get stream flow at each river segment, each blue line. And then top of that, we are working on with Andy Wood. We have over 2,000 corners USGS pristine sites plus. We collected Army Corps of Engineer plus US Bureau of Reclamation. They have a bunch of naturalized flow information. So we combine them. And then we just plot here to how it's distributed. So we can look at the little bit bigger river flow, at the flow at the bigger river like Missouri or Ohio, and it's you can look at. So that's kind of interesting to see what the flow looks like from CTSM. So back to CSM runs. So basically last 6 months or a year, maybe basically what I did is just like a bug fix existing Visual. I didn't do any new coding, but pretty much bug fix, and then able to run CSM3. But I use bcase, which is Mozart is running right now. Just swapping river models, just use Mizra. And I was able to 4 months because we didn't have a good PE layout. So I was able to only 4 months given 12 wall clock. So that's something I need help from Eric to, so I can run maybe future, maybe longer run to look at more. But anyway, that's what I have. And then, so there's a difference between Mozart and Mizra in terms of coupling. Mesh is Mizra use unstructured mesh. Mozart use 2D grids, so it's different structure. And then Mizra use only land mask, but the Mozart cover all globes, so land and ocean mask. And of course, routing physics is different, so that make it probably different result. So I just to take a look at what the looks like. So I ran only 4 months. So this is showing total discharge exported to ocean grid, so MOM. So I'm plotting discharge at the coastline, and then this is the MOM grid. So left is Mizra, and then right is Mozart. So you see immediately notice like Mizra missing Antarctica, and then couple of you see maybe Arctic, some missing runoff. So I believe I know why, but I don't want to talk about this. This is very technical thing, but I think I can fix it after this workshop. But I'm more curious about is Mizra has more discharge. You can see Mizra has more yellowish, reddish color than the Mozart. So that means like Mizra discharging more than the Mozart. So now I'm just digging into more the per ocean. So this is how. So we now looking at the discharge per ocean outlet to each ocean. So this is how discrete split in the globe in the ocean basins. Yeah, you can see a lot of brownish color. This is not connected to the ocean, but still like a river model has to send to ocean somehow. It's kind of funny thing to me, but that's okay. So now looking at the total discharge for 4 months for each oceans. So now I just now looking at the discharge went to ocean, but the discharge directly out exported from a river. So this is a little bit different because not before discharge entering coupler. So because of ocean discharge, discharge went to ocean was missing. So I just wanted to step back and then just looking at the river discharge exported from river model. So Just all I wanted to say is still Mizurat is more discharge as I expect. Some of, except the Indian Ocean, Mizurat is just less. Okay, so I still wondering why. And then, okay, maybe this is fully coupled run. So, because if you change one component, maybe just feedbacking to ocean, atmosphere, and then land. So that may be affecting runoff input. So I just looked at the global runoff input into river model. So you see a difference. But this doesn't tell me much. Okay, so 3rd month, 4 months, Mizurat getting more runoff, and then Mizurat discharging more. So, but the beginning of runs, Mizurat is less. So, okay, this doesn't explain why Mizurat has more discharge. Now I went back to run only coupling, so I can run a more longer run. So, and also fixing runoff input is same for Mozart and Mizurat. So I just run an I case. So this is still the same grid network. Just the difference is mostly like routing physics. So just looking at the like global total discharge at the outlet, you see still Mizurat has more discharge. But the interesting is, okay, river models store water too. So because of water is moving, so and then there's a residence time in the water in the river. So we can plot like a total river storage. That's the kind of telling something. So Mozart has more stored water than the Mizurat. And then that's kind of explaining like a Mizurat has more the discharging too fast. And then looking at the other studies, at the total discharge, global discharge is about 30,000 to 45 cubic meter per year. That's kind of ballpark for both river model. But storage is like, it's reported like 1,000 to 2,000, about 3,000 cubic meter per year. So it's kind of telling like a Mizurat maybe too low. So maybe too fast in a river model, Mizurat river model discharge, I think. So now I just need to go back in Mizurat, just river physics to see maybe you can change. So that's my last slide. So, okay, so things need to be done for Mizurat coupling. I didn't mention, but we need to create offline mapping between river and ocean. I wasn't aware before working on, but this is the most, I think Bill Sachs is here somewhere, I think. Yeah. He mentioned, okay, I need to do this first that's major things I need to do now. And then, okay, I need to work with Eric to change P layer so I can run CSM run and a bigger, longer run. So, and then I can do more robust water budget analysis. And eventually I'd like to use more catchment polygon structure grid. That's the benefit of using Mizurat. So that's the final goal, but it's getting there. So, so that's all I have.
Okay, great. Thanks. We have time for questions for Naoki, either in the room or online. You can put questions in the chat or raise your hand. We're always happy to hear from our online folks. Yeah.
How's the tracer work coming into there?
So it's kind of separate work. So I haven't done much, but after this, maybe. Or maybe I need this.
Yeah, go ahead, Peter.
So, great work. I'm wondering, like, some of this work's been done with reservoirs and reservoir management and irrigation. is Mesorat going to be released with that sort of functionality for CSM?
CSM3?
Or one of the versions of CSM going forward?
Yeah, eventually, yes. We know, yeah, we need to put the link. So I have to not the motor grid, but the catchment going on.
Mm-hmm.
That's need to be done before putting a link. Yeah, but still out.
No, yeah.
Seems like one way to resolve that, whether or not those differences in the runoff are real, is you can look at the large ensemble and just look at the comparative. Those are very short runs, right? 4 months.
Yes.
So it could just be some sort of, I believe it could be a feedback, not actually anything going on.
Oh, okay. Yeah, it's not 4 months long. It's maybe it's reading.
It's not totally crazy, I guess.
But yeah, it's yes.
Something coming over the chat.
Oh, yeah, sorry. So we've got Youngsu Zhang. Do you want to ask your question about sediments? Or maybe you can just take from that.
Yeah. Does Mesorat include sediment?
No.
But it does have traces, right?
Yeah, sediment, but you have to know what the coming out from riverbed. So river has to interact with better.
Mm-hmm.
That's not the
Yeah.
So on the discharge differences between Mesorat and Mozart, for Mozart, actually, the surface and subsurface runoff is like entering in different levels. Like one territories and the other one are
yes.
slopes. So do you think that somehow explain
actually yeah, potentially, but Mesorat has kind of similar thing. But I think more Mesorat has some. I ran a 1 day's time step. That's too cost. I'm suspect that.
Great, thanks so much. Let's thank Naoki again. We'll transition to our next speaker, which is Thomas Swenson, giving an update on hill slope hydrology.
Okay, yes, we're seeing if updated some of the recent work we did on the model.
Sean, can you turn the mic on?
The green lines on the top there.
Was that?
Okay, so just in case people don't know, what is the hill slope hydrology configuration? So basically it's this multi-column version of CTSM where we apply this representative hill slope concept, and that enables us to explicitly look at how water gets passed across the landscape, and also how the soil column and the stream channels interact, and then kind of importantly, it allows us to do some meteorological downscaling as a function of some of the hill slope properties. So typically slope and aspect and elevation. So that's what this cartoon is showing. On the left, basically how we're passing water along the topographic gradient, how we're modifying solar radiation based on slope and aspect in the center. And then on the right, we can do some elevation-based downscaling of things like temperature or precipitation amount, and then also precipitation phase, how those interact. So the first update is just that we've developed a methodology where we can essentially objectively calculate the hill slope properties directly from a DEM. So in the past, people would typically try to use these hill slope ideas, and they would use hypothetical hill slopes, or they would apply it to like a single catchment. But now we've been able to do this globally, and the paper describing that came out, I think, this summer, and you can take a look at that if you're interested in the methodology. Oh, and as well, we have the scripts, and Sam Rabin helped make those more usable for people to enable people to generate their own data as well. So what do I mean by the hill slope properties? Basically, every one of these columns now has these different hill slope properties. So for example, there's a width, a height, a slope, a distance from the stream channel, etc. And the way that we get those is we go to a high resolution DEM and we calculate things like, so in the upper left will be the height above the nearest drainage, and the right-hand panel will be the distance. And then we can calculate all these hill slope properties. If you look at the lower right, ultimately we come up with, like, for example, hill slope profiles. So elevation is a function of distance, as well as the other properties like the area and the width and all of these kind of things. And so every grid cell on the globe, we have data for all these different hill slopes, which is what this is showing. Okay, so that exists. In terms of what we've been doing with the hill slope model, most recently I've been working on prognostic wetlands. So in CTSM, we have surface water or ponded water parameterization, but in the past, due to sort of structural issues, it wasn't able to be used to prognostically or predict inundation, which is important for looking at wetland extent. And so instead, there was a observationally constrained inversion that's used in the model. But now with the hill slope model, we get this, essentially we get a number of different soil moisture states within a given grid cell. And so we can resolve lowlands versus uplands and wet areas versus dry areas. And so this has allowed us to in the future, it'll allow us to start using the prognostic inundation from the model instead. And there's various reasons why this would be interesting, but a particular interest right now is that these inundated areas are very important for modeling the terrestrial methane cycle. And so with this prognostic inundation, we can get a better handle on our methane model. So here's just an example of looking at the mean surface water from the model, which is at the top, and then comparing that to an observational estimate at the bottom. In this case, I'm looking at an update to the Global Lake and Wetlands database. And if you, broadly, you can see that the spatial patterns are quite consistent. And if you focus in on some of the major wetland complexes globally, you can see that we're really picking up a lot of the important wetland areas around the globe. And again, this is all predicted by the model, where there's no constraints and there's no tuning that we've done to try to get these spatial patterns. This is all coming essentially from the DEM, the global DEM that describes the land surface and its interactions with climate. And I don't expect to get much out of this plot, just to say, in a lot of these places, we're actually looking at the time series, and in a lot of these are all sort of the different wetland complexes that I had outlined. We're actually getting pretty good comparisons to some of the observations. And then a second point here is the different colors. You can see these different acronyms at the bottom. There's a number of different observational estimates, and there's actually quite a bit of uncertainty there. So one of the questions now is to sort of say, how do we try to adjust some of the parameters in the model to try to better match some of these observations given all this uncertainty? I don't really know what the right answer is. So that's going to be kind of interesting to come up with. But suffice to say, we're definitely kind of in the right region to start out with, and we have a pretty good handle on that now. The other thing I've been doing is trying to incorporate some machine learning methods to extend the information that's provided by the hill slope model to hyper resolution, if you want to use a buzzword. But basically what we have, I've been doing this in the context of snow. You could do this in terms of other variables, but what the hill slope model provides at every grid cell now is an ensemble of snowpacks. So before we had a single snowpack for a grid cell, now we have an ensemble of snowpacks, and each one of those snowpacks corresponds to different topographic characteristics. So it corresponds to your elevation and your orientation, whether you're north, east, south, or west, et cetera. And so we can use this topographic information and land cover information as predictors. And so we can train a machine learning emulator on these snowpacks with these predictors. And then we can go back to the original DEM, which could be, for example, 30 meters, and make predictions at those very high spatial scales. So this is a project I did with a colleague in Switzerland, Johanna Mahl, and for that we ran just over this regional domain, a half-degree simulation, and so you can see this is what a typical simulation would look like if you're trying to provide regional information. You sort of get well, this would be the spatial resolution that we get. And at the bottom, I've just applied, just from a plotting package, what it might look like if you decided to contour that. And that would be kind of the simplest kind of spatial interpolation that you could do. Now with the hill slope model, we have a little more information in that for every one of these grid cells, we now have multiple snowpacks. So we have more information there, but we don't have any more spatial information, right? There's no location associated with these representative hill slopes, but we do know that there's this ensemble of snowpacks that exist within each one of these pixels, and so we can use that. And when we do that, so this is just explaining that. So this is what the hill slope output would look like. These are just 4 different grid cells that I picked kind of randomly. And so you can see depending on what your elevation is and what your orientation is, you can see you get quite different snow depths for each one of these. And you get quite different seasonal cycles or snow season lengths for your snowpacks. And due to the meteorological downscaling, you can see in the upper right panel, I've created a perennial snowpack, which would be a glacier. So we take this and we train a machine, use a machine learning method, train an emulator, and then we apply that at very high resolution. And so, I guess this is sort of my workflow. But again, so we run this hill slope hydrology simulation, and the bottom left is just indicating that we have these different snowpacks. We ingest those into a machine learning emulator, and then the colored boxes would indicate the different geomorphic parameters, so elevation, aspect, slope, and then the target would be the snow value at the individual pixels in a DEM. So that's what you get when you do that. And so basically we can go from these kinds of outputs, and we do this post-processing step, and we can basically now at all these at this high resolution at any given pixel, we can say this is what our Earth system model, right? This is no longer, this isn't like a regional or high resolution simulation. This is still a half-degree Earth system model run. We can say this is what our prediction for the snowpack would be at any one of these locations. Johanna provided me with some output from a dedicated high resolution snow model that's well calibrated over the same region. And so that's what's shown at the top. And this is just a single time slice. But basically you can see we can do a pretty good job of replicating the kind of spatial patterns that you see in the very high resolution model, again, using our Earth system model. Some of the other applications that we've been doing this is one that I've been working with Summer Manala, and she's been kind of leading the effort of how we might use this technique to provide inputs to the glacier model. So now they have, in addition to the ice sheet model, they have they're applying the This is a Model 2 mountain glaciers. And so, for example, in this case, rather than giving these, and mountain glaciers are fairly high resolution, instead of giving the glacier model this coarse, say, 1 degree or half degree inputs, we can actually give it inputs at 90 meters or 30 meters. And so we can generate a time series of these very high resolution estimates of, this is snow depth, but it'd be the same for like the surface mass balance. And we can apply that. There. And then finally, another application that we're exploring, and this is with Andy Wood and Naoki, who just spoke. These are simulations that we've applied to the Front Range. So in these plots, the B is Boulder and the W is Winter Park, just to orient you. And we ran the model at, I think it was either 2 or 4 kilometers using the CONUS 404 forcing. And then we generated some even higher resolution hill slope data. And so then the idea here would be to try to run the model at these very high resolutions and then use the hill slope model to even further downscale down to something like 10 meters to force like a stream flow model. And then we can really try to see if that adds any value to the stream flow predictions at these very high resolutions. And this I think is interesting because I feel like if you can show people some interesting results that really connect to what they see in their, in their everyday life. For example, you look out the window and this is what we're seeing. And then you can say, we generated those predictions with the same model that we used to do our Earth system predictions. I think that's builds a lot of confidence, and going across these scales I think would be really useful to connect to people and to connect the science to people. So that's part of the reason for doing these really high resolution ones with the model. I think that would be an interesting outcome. So yeah, so we have hill slope data. The methodology's been published and the scripts are available, I think on GitHub. And so some of the things we've been able to do now with some of the new features of the hill slope model are these prognostic wetlands, which gives us wetland inundation extents. And then that's now going to enable us to do better prognostic methane simulations. And then we're trying to use the machine learning methods to do some, as opposed to interpolate in terms of space, we're trying to interpolate in terms of this parameter space to try to create a better estimate at these really hyper resolutions. I think that was it. I guess that wasn't it. So the future things I have to do are, I'm still working on calibrating the wetland and methane code. I need to improve some of my ability to do these machine learning methods and these emulation techniques. And that's definitely a place I would welcome input. I'm a novice in terms of doing that. And while it's easy to use some of these methods, you can kind of get any answer you want. So it's much more difficult to get a good answer. I'm interested in trying to apply these same kinds of ideas to some other quantities. I spoke with Lenny about maybe trying to do this same kind of idea for example, like carbon stocks for doing initial conditions. So instead of just trying to spatially interpolate, instead interpolate in terms of these other parameters to see if that gives a result that might not require the same sort of spin up times. And then, like I mentioned, Summer's leading this effort to try to create surface mass balance inputs that could be used for glaciers. So that's it. Oops.
Okay, thanks. Let's take one question if there's one in the audience.
Very interesting talk. I'm very interested in the work for the downscaling part from the although high resolution, but the very smooth features to the much more heterogeneous, especially the map. So I just wonder, is that the downscaling kind of work, or is it more like a emulation? You use an emulator, but to me it's more like a downscaling, right? You train a model from you train a machine learning model from coarse resolution simulations, and then you apply that machine learning model to a fine resolution. That's what you did, right?
Yes. It's not coarse resolution.
Well, it's a fine resolution, but it's very smooth spatially. So you want to have the spatial heterogeneity. That's why you have the a machine learning based model to show really nice mapping.
Well, really what it's doing is it's a different way of interpolating between these kind of quantities. So as opposed to, in terms of things where you like here, you're just interpolating in space and you get the smooth kind of version.
Yeah.
Here, you're not interpolating in space, you're interpolating in terms of these geomorphic parameters. And then the machine learning model is kind of filling in the gaps. So it's actually more analogous to what people do like in calibration, where you create an ensemble of all these different parameters, and then you use the machine learning method to try to fill up the gaps between there, so you can kind of quickly put that out to different combinations of those parameters. So each one of these snowpacks would have different combinations of elevation, and some are north facing, some are south facing. And now the emulator will allow you to kind of move between those to the values that you have at the very, very high resolutions.
Okay. Yeah, thank you.
Okay, great. Let's thank Sean again. And I'm sorry we can get to the questions online, but definitely keep the questions coming. We're going to move on to our next talk, which is going to be from Gordon Bonin on updates with the multi-layer canopy model. Here we go.
Okay, so this is a talk about the multi-layer canopy, but it's in the same spirit of Adriana's talk this morning about FATES, which is community modeling. So as I go through this, think about the way, does this help you with your science? What ways can you engage with this? And just as background of what this study is all about, there's sort of the big premise of this has always been that these big leaf models like CLM are incorrect but useful. And what I mean by that is the physics, the way they represent the system is not at all how the world really works, but it's useful because you can actually get the right answer out of it. And you can also run it globally for a 250-year climate simulation, and most of the time it doesn't blow up on you. So it's very useful, but you're getting the right answers for the wrong reasons. Something else that we haven't, and so what we're doing with the multi-layer canopy is saying, can we get a model that's correct and useful? And then with FATES, something to point out is CLM FATES is using a hybrid canopy. FATES is multi-layer for the vegetation tomography and for GPP. CLM is big leaf for fluxes and coupling with CAM. We haven't really talked about this too much, but maybe as people start working with CLM FATES, that'll become more obvious what's going on there. And then there are a series of papers that describe the model and these ideas with it. I'm going to show two results from our most recent study, which is for a walnut orchard in California. This is wind speed profiles for the month of May. The left is unstable conditions. The right is stable conditions. The model matches the observations really well. It doesn't matter. You can figure out which one of the observations if you look carefully, but it's a really good simulation. And why this matters is because wind speed affects the ease at which heat is exchanged from the leaves. So leaves in the upper canopy are exposed to much windier environments than leaves in the lower canopy. You can also think about maybe a crown fire is going to spread very differently than a ground surface fire or ground fire because of these different wind speeds. Another thing you can look at, which I thought is kind of fun, is like a sensible heat flux. Again, same thing, unstable conditions on the left. These are these are daytime conditions. And what you're seeing is in the observations is the sensible heat flux increases in magnitude as you go higher in the canopy. And then above the canopy, it's constant with height. And the model does a really good job at that. What's kind of neat is over on the stable side, these are nighttime conditions. And if you look at that very carefully, what you see is the lower canopy is a source of heat. That is, there's a positive sensible heat flux. The upper canopy is a sink, a negative sensible heat flux. And the model is doing a really good job at that too. But where are we going with this? We need more profile data. That was for a walnut orchard. Martin Belland has been working with Harvard Forest and Hubbard Brook data as part of the development of the CanVeg2 model. Sean Burns has data from Niwot Ridge, and there are other sites that have profile data too. It'd be very nice to see how different canopy structures shape temperature profiles. Because this is now the temperature profile for the walnut orchard, unstable conditions, meaning daytime. And it's the model does a good job, but it's also rather kind of boring. It's just this linear decrease with temperature with height.
If you go to other sites, you see something very different. This is some work that Matthew Wozniak did in the middle at the University of Michigan Biological Station several years ago. And if you look at the observations, what you're seeing is temperature is increasing as you approach the canopy from the top, and then within the canopy, temperature is cool. And the model is doing a very good, a good job of actually replicating that behavior, particularly if you look at like midday in the afternoon. Sean Burns has profile data for NIWAT. That's what we're seeing over on the far right. It shows the same thing, this mid-canopy thermal maximum. The model's doing a reasonable job of that. This is just an out-of-the-box simulation with generic parameters. But you're going to sort of see there's a formation of this mid-canopy thermal maximum. Some of the other thing we have with the profile data is CO2 profiles. Some of the sites have that. This is Sean's data for Niwot Ridge, again, in these daytime and nighttime conditions. And you can see if you look at the lower 5 meters of the canopy, you can see some really big, sharp gradients of CO2 between the surface and 5 meters in the lower canopy. And St. Martin has CO2 profile data for Harvard Forest that he's been using in the CanVeg model. And it's very easy to start modeling this because the conservation equation is exactly the same that you would use for temperature and water vapor in the canopy. The storage of CO2 in the canopy and the vertical flux divergence, balance the source sink terms in the canopy. So we can model this pretty easily, and that's one of the things we would like to start doing to see if we can actually get this right. Something else that you can do with these models, another project is biomass heat storage. Martin has incredible data from ground-based LiDAR data at Harvard Forest, where you're seeing you can actually see the image of the individual trees at the site. If you do a slice through that and look at the absorption of radiation, you can see very different patterns of absorption of radiation between the leaves and the wood. A big leaf model can't do that, can't distinguish between the leaves and the wood. It's all lumped together. And then you have to make some assumptions about how to disaggregate it, aggregate it if that's what you want. But in a multi-layer model, you can actually simulate the leaves and the wood. So that's kind of a neat thing. No model is perfect. This model has a really prominent bias. This again is the temperature profiles at that walnut orchard. The daytime on the left and then the nighttime ones. Let's look at the really strongly stable case, which is the purple line. And you can see that the observations are showing there's a cooling of the upper canopy at night, but then the air underneath the canopy is well mixed. If you look at the model, it's getting that upper canopy cooling, but it doesn't do the mixing under the canopy at all. And that's a well-known problem with these types of models. It uses a first-order turbulence closure, which doesn't allow for that strong mixing under the canopy under strongly stable conditions. In the CanVeg model, there's an alternative approach called a dispersion matrix, which uses principles of Lagrangian fluid dynamics. And so we're working with Martin and Tilden Myers at NOAA and Srinith Palluri at Texas A&M to see if we can if we brought these principles into the multi-layer canopy, how much would they alleviate this strongly stable bias in the model. So that's another project going on too. But what I want you to think about with this is that there's a sort of new emerging field in ecology called microclimate ecology. And what this is all about is that it's understanding the climate, the temperature, where organisms actually live. And it's focused a lot on overstory versus understory. It's looking at under the canopy versus open sites, and actually finding out the temperatures rather than looking at sort of the broad scale, large climate. It's actually the specific climate where organisms live. One of the tools to do that is this model of within canopy microclimates. And what this model is actually, it's a multi-layer canopy model written in R, and the community is using that to look at differences between overstory and understory and open sites versus closed canopies. And it's like, wow, wouldn't it be really fun if we could use CLM to do that type of work? If CLM could contribute to this new field of microclimate ecology, that would be kind of fun. So that's like a big picture, like, wow, could we get there? Well, what does it take to get there? And I've talked about this in the past, these software engineering needs. And it's just really worthwhile going through this again, because the challenge we have with this is that CLM is not modular code. And what I mean by that is there's no clean interface to surface fluxes. You're going to see things called canopy fluxes, soil fluxes, bare ground fluxes. Soil temperature actually calculates the soil fluxes. And then there's something called Biogeophys preflux calcs. It's all jumbled together and intertwined. If we just look at roughness, length, and displacement height, there are 5 subroutines spread across 4 modules to calculate roughness, length, and displacement height. So it's very hard to just sort of turn things off and replace it. Many of these modules do things in addition to the stated intent. Soil temperature has the urban model built into it. You'll see lots of if statements about different types of urban surfaces in the soil temperature code. So you can't just replace soil temperature or change it because you're changing the urban model too. Canopy fluxes calculates moisture stress, human heat stress indices, and other things. And then there's duplication of code across all these different for specific model needs, specifically with photosynthesis and stomata conductance, but also radiative transfer. And it's not just as simple as saying we would like to have one way of doing it across models. There are different radiative transfer models. Martin is using the Norman radiation to do the separation of leaves and wood. NOAA MP has a multi-layer canopy built into it, and they do 3D radiation. So perhaps we would like to look at those types of approaches too. In the past, I've likened this to the Kraken devouring the ship. I think that's still a useful analogy in that if the ship is not sinking, it's sort of dead in the water. It's hard to advance with these problems. I think a more interesting and helpful analogy is the Gordian knot. How do you unravel these complex problems? And I think really it's this duplication of code that's going to maybe provide a starting point. We can't solve everything at once, but maybe if we just start with duplication of code, we can start finding ways of building common interfaces across models. And then the last thing I want to end up with is just something I haven't talked about before at all, the software engineering of the multi-layer canopy model. There are 24 different modules that are used in the model, things like that define the data types that are used. The multi-layer canopy fluxes is the main driver of it. And then all these individual routines that do calculations, specific calculations. This runs uncoupled from CLM. There's dummy CLM code that provides the variables that are needed, but it's just sort of stub code. And then there's an offline driver to run it. And it's a very nice, simple way of doing it. You can just run it on a laptop or a workstation very easily. But you can also couple it directly into CLM. And that's something Sam Levis and I did a while ago now. You can actually take this code in the multi-layer canopy directory, bring it into a new directory as part of CLM, call the multi-layer canopy fluxes from that, and you're off and running. We did this for Niwot Ridge, like an 18-month simulation, just as a test case. The problem with all this is that you can't turn off the stuff above it. All that stuff above it is the flux calculations in CLM, and there's no simple way of turning that off. There's also no simple way of interfacing the multi-layer canopy fluxes with all the other parts of CLM. So what I mean by this is just prototype coupling. It runs parallel to the existing surface fluxes, but it does not overwrite the surface fluxes. So it's a very limited coupling, but at least I think provides a starting point for people to say, okay, well, how do we actually solve these problems? And so it's designed with that in mind, is to be a starting point. But I want to end with this idea. How can the land model working group contribute to this? Hopefully you'll see there's a lot of interesting science that can be done. Again, what I want to emphasize is it's a research model. It has very limited sort of cases, flux tower cases. It's very much oriented around process studies, identifying what processes are important to get the right answer. It's very much a hands-on model. You got to get your hands dirty to do this. You have to write your own output files. You have to figure out what variables you want to look at. But I do think that there's an opportunity of cutting the Gordian knot. The solution to the Gordian knot was not to painstakingly unravel it. It was to take an axe and just cut it, and then your problem solved. I'm not saying we have to take an axe to seal in, but I do think, we have to think outside the box. We don't, if we let the Gordian knot sort of overwhelm us, we'll say there's nothing we can do. And we have to find clever ways of sort of unraveling the knot. And I'll just leave it at that.
Okay, thanks so much, Gordon. We have some activity online. So I think, did I see the chat question come in first? Can we pull up the chat in the room? Thanks. Yeah.
Chuck's question was first, which is the top question. Chuck, do you want to ask the question, or do you want to just go with what you put in there?
Yeah, so I showed the sensible heat flux profile because, well, first let me back up. Very few sites actually have profiles of fluxes within the canopy. Those are hard measurements to make. I showed the sensible heat flux one because I like it, because you definitely see in these nighttime conditions this difference between a source of heat in the lower canopy and a sink in the upper canopy. At the Walnut Orchard, we have the same measurements. The same measurements were made for evapotranspiration. And you see very nicely the model, the increase in evapotranspiration as you lower latent heat flux as you go higher in the canopy. So yes, the model can do that. And that's one of the big things we can do in the model, and then that feeds back on the water vapor profiles within the canopy.
Let's hear from Wanton Lee, and then Josh, if you put your question in the chat, because we're going to have to move on after this discussion. Thanks.
Okay, great. Thank you very much. Gordon, your very nice talk. I have one or maybe two questions. The first one is related to the multi-layer evaporation. So I'm wondering, it's very impressive to see you have quite great matching between observations and simulations about the vertical heterogeneity of air temperature. And is that the result simply from the correct wind speed related turbulence model, or it is also a combination between turbulence and the energy balance for each layer across the vertical canopy? That's my question.
I think it's a combination of everything, because you have the net radiation profile through the canopy that's driving sort of leaf temperature and surface fluxes. You then have the stomatic conductance profile through the canopy. I do think the wind profile is really important, because what you're seeing is leaves in the upper canopy are exposed to high radiation, and you would think they'd be really warm, but they also are exposed to high wind speed, so it's easy to dissipate that heat. Whereas you go deeper in the canopy, you get less radiation. Perhaps the leaves should be cooler, but you have a much lower wind speed, and it's harder to dissipate the heat. So I think the wind profile is very important to this. There's just been no way of really sort of turning things off and sort of saying how much is the vertical profile associated, say, with wind speed or radiation or stomatic conductance. But I do think
so it is a consequence of the energy balance for each layer as well.
Yeah, because the wind speed is all part of the whole the simulation. The wind speed profiles depends on the drag within the canopy, the absorption of a momentum, the stability and the coupling between the canopy and the atmosphere. And all that then factors into the energy fluxes too, which affects then the coupling back with the atmosphere through stability. So it's a coupled system, and it's hard to disassociate these things or disentangle them. But I think the wind speed is really critical.
Okay, fabulous. Thank you very much. Can I have another question? Very short one.
Yeah, we've got to move on. Maybe you could put it in the chat. But thanks so much, Gordon. All right, so next we're going to hear from G.E. Joe, who's going to talk also about multi-layer canopy in the context of stomatal conductance models.
Hi everyone, I'm going to talk about my recent work on comparing multiple stomatal conductance model in multi-layer canopy simulations. Stoma control both carbon and water fluxes, playing an important role in ecosystem and atmosphere exchanges. Because of this, many studies have tried different ways to model stoma. And early models are mostly empirical, linking stomate directly to external environmental variables. And the paper in 2010 reviews 35 empirical stomatal conductance models. And some of the empirical models are still widely using now. And another group of model is optimization models. And the optimization model assumes that plan open stomate to maximize net carbon gain, that is balancing the carbon gain and the water penalty. In the optimization model, the carbon gain is usually represented by photosynthesis, but the penalty term differs. Some optimization model treated penalty based on water supply, and some based on xylem vulnerability, and some others based on stomatal limitations to photosynthesis. Because they are all solving numerically, so some of them have their analytical solution or approximate solutions to improve computational efficiency, such as the metal model and the analytical solution of the L model. With so many optimization available, so it is nature to ask which optimization model performs better, and many studies have tried different ways to evaluate this model. And one, in their studies, they said it is 7 theoretical criteria and found that only xylem vulnerability-based and no stomatal limitation-based optimization model meets more than 6 criteria. And also they also based on the all these models' performance for photosynthesis and transpiration, and they found that the xylem vulnerability-based model have better performance. However, another study shows different conclusions, and they found that the optimization model based on water supply have better predictive and functional performance, and also has better constraints parameters. And also there another study compare both empirical and optimization model, and they use it for metric to compare these 12 models, and they found that the top performance, the best performing models are highlighted. So we can find that they are all optimization models, and mostly are xylem vulnerability-based optimization model. And for the metal model, it is as a default stomatal conductance model in CLM. We can find that this optimization model perform better than metal model. And also they also show the parameter uncertainty ranges for this optimization models, and we find that they find that the xylem vulnerability-based optimization model has their parameters are well constrained. And all the paper are reviewed, they're all based on leaf level simulations. So if we want them to apply on the land models, we need to consider canopy process, leaf to canopy scaling processes. So will this model still perform well? So how do this stomatal conductance model behave in canopy level? And there are 2 canopy approach. One is big leaf approach, treating the entire canopy as one layer, and it is often used in large-scale land models. And another is going to talk about the multi-layer canopy model, and it explicitly resolve canopy vertical structure, and we can have a deeper look. We can have a detailed look into the the multi-layer, the stomatal conductance interacting with environmental variables. So in this work, I'm saying how the stomatal conductance model behave in multi-layer canopy model. And we use the Golden's multi-layer canopy model, and there are 3 stomatal conductance model already included. The Bowberry model is empirical model. The water use efficiency model is a water supply-based optimization model. Metal model is derived from water use efficiency model, and it has a very similar format with Bowberry model. So we group these three models as blue group, and we added two silent vulnerability-based optimization model. And based on the previous research, they're very promising. And we added two more recent stone metal conductance model based on recent understanding on stone metal physiology. And we treated them as red group. We're testing this stone metal conductance model in the University of Michigan Biological Station. And here is the dyno cycle of lantern heat and GPP over this site during June to September. And these are their simulations results. We can find that all this stone metal conductance model falling within one standard deviation of observation, and they all show comparable explained variance to observed lantern heat and GPP. So these models are well performed, and since we're using multi-layer canopy model, it's interesting to see their vertical profile. And this is the stone metal conductance vertical profile from metal model. The shading shows the GS values. The black dots shows the peak GS timing, peak GS position. As we do not have many stone metal conductance vertical profiles, so we use the metal model as reference. And we can find the GS peak timing occurring in the morning and the GS values decreasing along the canopy. And compared to other models, we can find that the Bowberry and water use efficiency model is very similarly to metal model. These two optimization models show somewhat similarity, but the two most recent models are not similar to metal model. And there are two key features to note. One is the GS peak timing. We find that for the blue and green group, their GS values all peak in the around 7 to 8 a.m., while for the Buckley and Podkey model, they're occurring in the afternoon. Also, more specific is for the Podkey model, there are high GS values in the lower canopy in both ends of the day. So I'm just wondering, why do different GS models peak at different times of day? And so I think of that the solar radiation varies greatly within a day. Well, it's because of the different GS sensitivity to their light responses curve. So I do a sensitivity experiments by changing solar radiation levels, and we can find that the Podkey and Buckley model reaches their higher GS values at very high lights, while other models show clearly banding or saturating around 200 watts per square meter. So this could explain why blue and green groups that their GS values peak in the morning time, while the two peak in the afternoon. And also why the Podkey model shows high low canopy GS at both ends of the day. Still, I think it's because of different GS responses to their environmental variables. And when I look at the GS responses to VPD, I find that the Podkey model in their low canopy, it has a very stronger negative correlations. This means the GS will increase when VPD decrease. While for the metal model, it shows a weak positive relationship. And it is also for Bowberry water use efficiency and Buckley model. And in the one and Sperry model, it shows very weak relationship. So the distinct pattern for the Podkey model in their lower canopy might explain why this model is different to other models. It is possible in the morning or evening time, the VPD is very low and they're just trying to open as much as they can. And this all my preliminary results, and I got some conclusions for them that all these models show good skills. But my analysis is based on only one side, and I didn't test them how they respond to heat and water stress. And we also find that the peak GS timing differ across stone metal models, and the particle model shows very strong sensitivity to VPD. But the thing I'm trying to do is to be more to calibrate these parameters and considering this parameter uncertainty before I move to other sites. And thank you.
Great, thank you so much. Do we have a question in the room? Okay, go ahead.
Yeah, so it's very interesting work. When you look at the positive versus negative relationship between stone metal conductance and VPD, have you controlled the other variables? Yeah, I think controlling other variables is very important before you look at their relation with the VPD. Yeah, and I also suggest looking at the not only the diurnal cycle, but like drought versus normal conditions, because their response to VPD can be different because the time scale is different.
Yes, that's what I'm trying to do, like to control all the variables constant, like to explicitly see their responses. I'm trying to show their responses to different variables, like to G, to CO2, solar radiation, temperature, and VPD. I don't know, some models, they do not very, it's still hard for me to explain that. So I'm still trying to better understand their performance and to get a better idea. Thank you.
Okay, I think are those both the previous talk? Or?
No, one is for this talk. All previous chat is for the previous talk.
Okay, thanks. Let's quickly take this last chat question. So, interesting work. Is there any tests related to soil moisture regulating through GS?
Oh, yeah. This is the thing I want to do, but it is hard because soil moisture has so many layers. How do I simulate the drought experiments? I don't know how to better to have them regularly changes, like decreasing. Yeah, I hope I can have a better idea about how to do this. Yeah, I don't know how to do this.
Great, let's thank Judy again. Okay, our final speaker is online. It's Aya Lalu, and she's going to talk about translating CLM ML to JAX. Aya, are you there? Can you share your screen?
Yes, I'm here. I'm sharing my screen at the moment. Okay.
Okay, great. Go ahead.
Yes. Hi, everyone. My name is Aya. I am at Columbia University. I work with Pierre Gentine. I was here a few months ago as well. But today I wanted to show some work that I have presented at the Atmospheric Working Group, but I would like to share it with you all that would have more understanding of the CLMML. And so I'm glad that the two presentations before me covered a lot of ground on that. So what I want to talk about is specifically the motivation behind this, which is the technical debt that there is in a lot of Earth system models, specifically architectural challenges with, as Gordon said, that a big knot of like complex nested hierarchies, as well as extensive module level global states with hidden dependencies and other challenges of this kind. Other barriers are ML integration barriers, making more novel or data-driven parts that could be beneficial for our system models, not readily matching the code bases that we are developing like models in. And another motivation of this is really to shoot for differentiable models and accelerate the computation of a lot of these models. And so with that in mind, we came up with a pipeline to use large language models for an automatic translation, validation, and repair of legacy Fortran models. Specifically in this pipeline, which I'll go in more detail in the next few slides, covers first a static analysis. So needing to have a big understanding of what this code base looks like and what are the dependencies and the links between like each of the modules. And then with that in mind, also, how do we break down large modules that need refactoring? How can we feed them to an LLM to ensure that our translation or our generated tests or refactoring later on will be well done. The next step in the pipeline is the actual translation. So the first pass of the Fortran code, as well as all the static analysis information that we have gathered. So dependencies and translational units. And then once that is done, we have a third agent that is called a testing agent, which generates tests, specifically PyTest suites for the Python translation that has been generated. And then after having the tests, we run them. If in the case of a failure of tests, we then call on a repair agent, which takes on the Fortran code, the Python translation that was given and failed the test, and fixes the test based on the logs of the test suite that were failing. And that's an iterative process, so we can fix it to a certain amount of repairs, run the tests again. So as long as it's not passing, we can iterate again into the repair. So to talk a little bit more detail about the static analysis, we made a tool called Fortran Analyzer, which is a custom framework to generate these outputs for this pipeline. This framework uses FPARS and networks, which are libraries that parse through Fortran code and can generate a good understanding of the dependency analysis. So specifically, it generates module dependency graphs. It also detects any circular dependencies. And then for the translation unit decomposition, we here try to break large procedures into smaller chunks. Specifically, we can separate our modules into different subroutines, but what happens when a subroutine itself is too large to translate accurately, then we have a way to decompose the subroutine in chunks, specifically around loops or nested loops and so on, just like it's shown in the right-hand side of the slide. And so we get two outputs from this custom framework: the module dependency, so a JSON file that just has all the module names, and also the dependencies inside of that module name, the number of lines, the file path to the specific module that we want to refactor or translate later. And similarly, for the decomposed translation units, we have an output JSON file that has a specific module, and then how many units is it further separated in. So this is just a little more information about how to decompose the translation units, and some of the papers showing the success rates of LLMs translating code based on the length of a specific function. Specifically, the larger the function, the larger the number of lines that we pass to an LLM, the lower is the success rate of the translation. And so that was the motivation for decomposing into different units. And this part right here is about the motivation behind the dependency graph and analysis. And this is specifically to have a topological sorting order of the translation. So we start with a bottom-up approach, translating first all of the modules that are used by others but themselves do not call on other modules, so that the LLM can add that into its context and would not have to guess a structure of, let's say, a dependency of a specific file that we are translating. And so that reduces the hallucination risk of the LLM when trying to translate them by approximately 30.8%, which is really quite important. And so this is what the dependency order translation looks like. We have a graph with all of like our translation units and start from the bottom up. Next onto the translation agent. This is an iterative context accumulation given the translation units. So we translate one translation unit at a time in each module, and then finally do a final module assembly pass just to see if everything makes sense with how the translation units were translated and concatenated, and that there is a consistency across all variables, across all units, and so on. And so for, as an example here, for translating the soil temperature mod, we have like it was divided into 8 translation units, and we added an assembly call to look at all of those concatenated units. And for that specific module, the translation call, for example, was 56 cents. And this will make sense later. For the testing agent here, it's specifically useful when legacy unit tests are not available. So it was the case here. And then it helps also build a test suite for future development, regardless of the initial refactoring. So it can target typical operating conditions, edge cases, boundary conditions, physical constraints, and so on. And then finally, for the repair agent, the motivation here is that research shows that about 45 to 73% of first pass translation success rate. But so about 25 to 55% still need repair. And with an iterative repair process, it increases accuracy after each iteration. After the one repair iteration, we are at a 65 to 85% success rate. And then after 2 or 3 iterations, it's about 80 to 92% success rate. However, it shows that after 3 iterations, it starts to stagnate or plateau the number of like the improvement from one pass to another. So that would be like a good time to look at it manually and reassess. And I just wanted to show a little bit the end-to-end pipeline. So when I tried to run the pipeline for the canopy state type module, as you can see, like at the top of this, at the top here, I'm running it for specifically the canopy state type. And so once I run that command, all the steps like fall into place one at a time. So it can show you here the first step being the translation. So it translates each unit at a time. Here we have 3 translation units. And then once all the translation is completed successfully, we go on to the second step, which is the test generation. This is something that the LLM just does automatically from like one step to another. So once the test generation is complete, all of the test files and the test data, as well as some documentation, is saved. And then we're able to run the test. Here you can also see the cost example of the test generation is specifically 34 cents for this module. So we can run, or it runs the tests automatically after. Here, some tests have failed, so the repair agent came and started running a repair process. So this is how this pipeline works. It does reduce significantly the need for iterations between like a human and a machine, or the LLM, and can do the iterations for the repair also automatically, and look at the specific tests that are failing. All of this like in very short amount of time. I believe like for one module, this took I think like less than 2 minutes. So it does like scale up when we're thinking about refactoring like larger code bases to be able to do them a lot faster and a lot cheaper is really great. Great motivation here. I finally wanted to talk also about like some ways to improve LLM translations, testing, and repair. And specifically, this is prompt engineering. So I'm sure like a lot of you have heard that generally from just messing around with ChatGPT or Claude on your own, but prompt engineering for an LLM, like when using like an API, is also very, very important. Here we can have a context augmented like prompt structure where what like our work with the static analysis like makes a lot more sense. Here we can add all the dependencies of our code base, and also the previously translated units to have that context accumulation. But also, most importantly, is the requirements of the specific translation. If we're going from Fortran to Python or from Fortran to JAX, there will be like different requirements. And so it's very useful to be as specific as possible with the prompting. Specifically, if we are, in this example, we really wanted like a differentiable model, and like to use JAX to make to run the CLMML in a differentiable way. And so I saw that like after a few iterations of the translation, being as specific as possible with every single modification that like would go from, just basic Python to actually this is the JAX equivalent that would allow this code to be differentiable, was really necessary and important in the prompts. And yeah, from the same paper that I've been citing earlier, effective prompts or improved prompts can like show up to like 3 times like better results and success rates in first pass translations. And so about the differentiability question, I have tried a smaller tests case with the mixing length module in Club, which is a part of CAM. So these are the specific parts that I was saying about like making use of every functionality of JAX to make this differentiable. Specifically, how do we deal with loops, and then how do we deal with conditions and nested like column level iterations and etc. So all of this was further like specified to the LLM like once we've found out about that. These are just some preliminary results like from the translation of the mixing length, and it had achieved over like 100 times like speed up with like a GPU, which was really nice. And the results are quite comparable to the Fortran results. So that was a good motivation to keep going with this. And so for the part about this CLM multi-layer canopy model, this was specifically used because it would achieve like a really big savings in terms of computational cost. The CLM multi-layer has like 5 to 10 times the vertical resolution increase compared to the big leaf model. So it was a really good candidate for GPU acceleration. And in terms of like practical advantages, it was really nice to be able to like run it offline and compare it to tower sites and have the validation data available. And so for this project specifically, the work is still in progress. Results will be coming soon, hopefully. But this is the GitHub that hosts the JAX version of the CLMML v2 at the moment, and I hope to show you more results very soon. But I'll leave you with some of the results, some of the lessons that I've learned in here, which is, again, if you have a modular or if you are able to pre-modularize like your code base, it really will help a lot in breaking down your code and making it easier to translate using an automatic LLM pipeline. Very specific prompts are very, very useful. And they have, like, for me, achieved like the most progress in getting better translations. Test-driven translation, here, like specifically having test guide validation at each step. So this is something that I've talked to a lot of people about and want to do myself, which is to use crocodile clips for high order like functions. So to save the real input and output data from the Fortran simulations after each like high order function to guide the testing agent, for example, and not generate our own test data. And other methods that I've seen around was to create like single test suites that can target Fortran or Python. So being able to use the same like test suite to run specific Fortran modules and compare them with the Python as well. Yeah. And for the next steps, I still have to do some offline testing and validation, and really hoping to run this as well with a couple of runs with the CLM5, and looking forward to like look at the performance benchmark, specifically comparing what we gain from Fortran or JAX CPU and then JAX GPU. And maybe if all this goes well, look into a full CLM6 refactoring now that we have a lot of these modules already translated. And I'll just leave you with this summary, and I'll take any questions.
Thanks so much, Aya. We are running into the break a little bit, but I'd like to see if there's one quick question for Aya. I have one, which is, you mentioned cost, like in terms of currency. Can you talk about how that worked into this, how that came into this workflow?
Yes. So after each step in the base agent, essentially, of the pipeline, we're just keeping track of the cost. So we're not using a, I guess like an API like Claude, or like not using Claude or like ChatGPT on like the actual website or software, but using an API key. And so that is able to track the cost after each specific number of like inputs and like outputs given. So specifically for the translation, with when we're giving a specific Fortran module, if it is very large, it will then like cost like more money. So that's like how we can track how the cost will scale with like a smaller example. But for the base agent, it does save the cost after each translation or test generation or repair. So we're able to look at all of that at the end. And so with the translation testing and different repairs, it usually came about like $2.50 to $3 per module. And this is like, I'm not counting any like exploratory runs or errors on my side.
Okay, great. Thanks, Aya. All right, well, it's time for us to take a break. Let's thank all of our speakers.
Hello, everyone. This is Aman Shrestha from Michigan State University, and I'll be talking about integrated hydrological crop irrigation modeling using CLM5. So I'm a PhD student at Michigan State University. My advisor is Dr. Yadip Pokhrel, and I'm working on an NSF-funded project to irrigate or not, which uses CLM5 to model the feasibility and need of irrigation and agricultural adaptation in the Mississippi River Basin. So to that end, we use a 5-kilometer scale regional biogeochemistry CLM5 simulations with transient land use, regionally tuned parameters. I'll be talking about more about this model setup in the next slide. So we are interested to holistically look at hydrology, crop, and irrigation modeling to advance the performance of CLM5 to model past trends and variabilities. And also a second part of this work is to assess the need of irrigation expansion in the Mississippi River Basin to sustain crop production under future climate scenarios. So this will be towards the end of the presentation. So here we have a map of the Mississippi River Basin. It covers around 3 million square kilometers and is one of the most agriculturally productive regions in the whole world. So the Mississippi River network is shown with 6 subbasins. Highlighted in gray is the High Plains Aquifer to the left and the Mississippi Alluvial Plains to the right, which are 2 intensely irrigated regions in the Mississippi River Basin. So to model this region, we force CLM5 using CONUS 404 atmospheric forcing, using regional surface data and regional parameters. We configure CLM5's hydrology to use regional parameter values. We configure the crop model to use regional parameters for rain-fed corn and rain-fed soybean. And we also configure the irrigation module to include the drip, sprinkler, flood, paddy irrigation techniques work done by Yao, which I believe will be incorporated in the next release of CLM. Also, we apply a new module within the irrigation system that is to partition the surface water and groundwater withdrawal. We use the Mozart river routing module at 1/8 degree resolution, and we look at stream flow, crop yields, and irrigation withdrawal. So starting with hydrology, we have a map of Kling-Gupta efficiency, which compares modeled stream flow versus observed stream flow at various USGS stations across the Mississippi. So we see a clear east-west contrast with the eastern side showing good, moderate to good KZ performance values between 0.5, 0.7, and the west showing poor performance. So looking at individual stations, we see seasonal hydrographs with the black line showing observed stream flow and the blue line showing modeled stream flow. We see really good match between the modeled stream flow and observed stream flow for like stations in the eastern side versus in the western side, we have really poorly for performing stations. So our next task was to improve the stream flow performance. And in the absence of the work that Son just discussed this morning about spatially distributed parameters, we opted to adjust 3 most sensitive parameters based on past sensitivity studies. So these 3 sensitivity parameters were adjusted based on prior ranges from past literature. First, we use Fmax, which is a spatially distributed parameter, which is the maximum area in a grid cell, which can be saturated, and then supply surface runoff. So in this hydrograph, the black line shows observed stream flow. The blue dotted line is the default stream flow model by CLM5. And so we scale Fmax with a scaling factor of 0.75 to 0.25. Scaling Fmax changes the base flow response of stream flow without changing the peak stream flow response. And we also, after selecting the best value of Fmax, we apply a chain rule, that is, we select the best parameter value and then opt to adjust for next parameter, which is Dmax, which is the dry surface layer thickness, and relates to the resistance of soil to evaporation. So we select value of Dmax equals to 10 millimeters, and then adjust for Wattsat SF, which is a scaling factor for soil porosity or the maximum amount of water available in the soil. And Wattsat SF is most sensitive. The stream flow peaks are most sensitive to SF, and we select the value of 1.4. Here we have a number of different stream flow stations, and the performance is consistent among all of the stations, except for like the Missouri River, because CLM5 does not model dams, and there are a number of high capacity dams in the Missouri rivers. So moving on to crop models, we have a map of the most dominant crop types in the Mississippi River Basin. The Midwest is mostly corn, soybean, and then wheat. So we have collaborators from UIUC, which provided us calibrated rainfed corn and rainfed soybean parameters. The parameters were mostly related to plant hydraulics, photosynthetic capacity, planting temperature, and the parameters were calibrated for county level annual yield in the US Midwest. So there's a table of the default and calibrated corn and soybean parameters. I'll just skip that. And so the calibrated crop model with the calibrated parameters provide us better yield averages and better trends compared to the default model. So in the table we see, like, for instance, for rainfed corn, the default trend is 0.9 versus the observed trend from USDA dataset is 12. We were able to improve the trend to 7.5 without seriously impacting the RMSE score or the correlation score. We substantially improved the percent bias in both rainfed corn and rainfed soybean yields. So looking at spatial pattern of these biases, we see, like, some counties overestimating these yields, which are in blue, some counties underestimating yields. But looking at an overall annual time series, the model yield is able to match the observed yield trend, but the interannual variabilities are overestimated. Also, we have similar performance for rainfed soybean with, like, the model yield matching the trends, but with more interannual variation. But, like, looking outside the Midwest, we see degrading performance for biases and trends in both the Highlands Aquifer, the Mississippi Alluvial Plain, and this is, like, as expected because we calibrated for the US Midwest, the agriculture systems, management system, and the climate for the US Midwest. So this is expected. So moving to irrigation in the Highlands Aquifer and the Mississippi Alluvial Plain, the default CLM5 irrigation model severely overestimates irrigation. So the blue line shows modeled irrigation withdrawals, and the black line shows observations. We investigate that and find that irrigated paddy consumes a lot more water. So this module uses a paddy 3 irrigation configuration, which is paddy is irrigated whenever the soil moisture falls below saturation. And we change this configuration to only irrigate whenever the soil moisture in the paddy columns are below a certain threshold, which is similar to all other irrigated crop types. This effectively decreases the frequency of irrigation. So I compare, like, different irrigation withdrawals for different plant types and find that the purple line, which is for irrigated paddy, is substantially reduced. Still, there are a number of issues remaining. Like, the first is that the surface water and groundwater irrigation ratio is imbalanced. The second, like, total irrigation withdrawals are overestimated. The third is that irrigation timing is 2 or 3 months earlier than what's actually happening. So first, we investigate the surface and groundwater partitioning. We create a new module which uses a ratio of groundwater to total irrigation withdrawal at each grid cell. So this map shows the actual data set. So we see the central US is most, like, heavily groundwater irrigated. We add this capability in CLM5 and then test the performance of this module for 2010 and 2019, and we see substantial improvement and simulating surface and groundwater irrigation in the Highlands Aquifer and in the Mississippi alluvial plains. Also, to address the issue of total irrigation withdrawal, we set the irrigation threshold to 0.5. Here, the first row is seasonal irrigation. The second row is seasonal surface irrigation. The second row is groundwater irrigation, and the third row is total irrigation. So we find that the surface water to the groundwater withdrawal ratio has improved, except for this, the first panel for the Highlands Aquifer. And I think this is related to like not having spatially distributed irrigation threshold parameter. And we're able to match the total irrigation withdrawal to USGS observation, but we still have the issue of timing. So to investigate this, we compare irrigation with total leaf area and crop area, and we see that the total leaf area and the crop area matches with irrigation peak. So we hypothesize that like changing crop planting windows will also change the irrigation timing. So we run some tests by changing the default crop calendar. We shift the default crop calendar by 60 days. So in the bottom two panels, we have the red line showing irrigation for default crop calendar, the green line with crop calendar shifted by 60 days, and the observed timing. We see that the irrigation timing has changed, but there's an unintended consequence that there's a change in irrigation quantity. So this links to the fact that there's farmer decisions to irrigate are difficult to model. So finally, using this refined regional model, we're trying to assess the future water availability in rain-fed crops. So we force CLM5 using 5 GCMs under 3 scenarios. We calculate water use efficiency. We also develop a logistic growth crop model to estimate future technological trend. We add the climate trend and variability from the climate models and calculate future crop yield. Then we calculate future water need and future water deficit. So this is just showing the temperature trend in the future for different scenarios. It's increasing steadily in the future for all scenarios, and VPD also shows the similar increasing trend. So we have rain-fed corn yield changes and rain-fed soybean yield changes. We see some increasing trend for the northern and southern part of the Mississippi, with some decreases in the middle part of the Mississippi. But for rain-fed soybean, it's increasing. Therefore, I see increasing rain-fed soybean yield. We have similar water use efficiency pattern for both rain-fed corn and rain-fed soybean. So finally, we calculate areas facing frequent water deficits, which is, we calculate water deficit as if an area has less precipitation than what is needed to sustain crop production for more than 75% of all the years. So the areas in blue, so areas facing water deficit in the near future. The area in pink shows water deficit for the far future. And we see most of the Midwest, the Mississippi, may need irrigation in the future. And that rain-fed agriculture might not be sustainable in the future. We also see the similar pattern. We see a strip of area facing frequent water deficit in the Highlands Aquifer in the Mississippi alluvial plains. That's about it. Yes. I'd like to thank my collaborators, Mingti, Ashraf, Mirzet, Kayu, Sam, Danica. Thank you.
Thank you. Very nice presentation, but we have to move on to the next speaker.
There are questions for the discussion. And our next speaker, Tom, yes, and remote. Yang, are you online?
Yes, I'm here. Could you all see my slides?
Can you share your screen?
Yes. Sure, yes. Okay, could I see?
We do see your screen. If you put it in presentation mode, that's all.
Yes. Okay.
Okay, I put it in presentation. No, that's the last one.
Could you all see my slide now?
Yes.
Okay. So, okay. Thanks for the introduction. I hope I could be there in person, but I have to teach this morning. So today I would like to talk about some of our effort. So how we're using AI and also the multi-scale of the data and to better represent the soil degradation process in the CIM. So the basic question here that is actually very common for most of the Earth system models. So the big uncertainty here is the soil carbon degradation. And if we look at that, what is the main challenge here, that is how to represent the basic soil turnover time. So the currently in CM and most of the Earth system model, the degradation rate will be regulated by the empirical equation of the temperature, soil moisture, oxygen. And the issue is that most of the equations here are more empirical, so maybe it's a little difficult to be expanded to the larger scale. And we also know a lot of those processes regulated by the microbial community, but has not been well considered here. So the two important missing mechanisms here is one related to the resource allocation strategy of the microbial community. So basically, the biologists, the ecologists, they already hypothesized that microbial community, they can shift, trying to optimize their basically the antigen and also the resource allocation strategy so that they can satisfy their need of the growth, resource allocation, and also the stress mitigation. But also they hypothesized that may be related to what the environmental condition happened in the past. So the figure here just showing the conceptually maybe the soil drying process, how long the drying will be, and even how fast the drying will be, will affect a lot about that the microbial community, how they will respond to the soil moisture process. But those kinds of mechanisms had not been well considered in the all the Earth system models. Another mechanism that had been considered in the some set level soil biochemistry model, and that is related to the basic mineral absorption process. So we know that if we look at the basically the particular of the soil organic matter, they have those basically can be absorbed by the minerals, so that they usually not be easily to be touched by the microbial community. So can this we call the usually as the mineral associated organic carbon, they can make a soil carbon relatively stable. So that process is the mineral absorption basic protection. This has not been well represented in the Earth system model. The main issue is that we didn't have the data to benchmark the fraction of this mineral associated organic matter on the larger scale. So basically our study here trying to focus on these two questions: how we can better understand this environmental heterogeneity, their regulation on this mineral adoption process, and how the historical and the present hydrothermodynamics will further regulate the resource allocation strategy of the microbial community. Finally, how that may be affect on the soil carbon degradation and the stability. So in order to answer this question, we designed this hybrid model framework. So in our component, this model, we're using the CM as one of the Earth system model as an example. So we have a machine learning pipeline that can use to benchmark that how the environmental factor will regulate the fraction of the mineral-associated organic matter. That can also inform another machine learning model to interpret that how the environmental regulation the resource allocation strategy of the microbial community. Then we can using all those models also to predict basically the larger scale of the graded version of the data to showing the fraction of the mineral associated organic matter and even the basic microbial functions. Then we can incorporate those information into the basically the CM model to represent the original those F temperature, F basically the moisture, those equations to indicate the environmental regulation on the decomposition rate. And we also built an AI-based surrogate model to mimic the soil decomposition process in the CM. Then we can using this model to more efficiently kill the parameters related to those new functions we introduced. So I will introduce this one by one. So this is the work mainly done by my student Sabrina. So we first using a global scale of the data that includes the mineral associated organic matter fraction and also the corresponding environmental data across the basically the global scale around 1,000 amount of data. We're using this data to train basically the random forest model, trying to understand how the environmental condition will regulate the fraction of the mineral associated organic carbon. So finally, we filter those very important factors like the mean annual temperature and the mean annual precipitation to the basically the potential ET ratios and also the soil texture condition and the soil organic carbon soil saline ratio. So the figure here just showing the using to interpret the machine learning model result that is showing as accumulated local effect of each individual environmental factor. So basically that tells us that under if the soil fraction is higher, and that can introduce a high abundance of the fraction of the associated organic matter. So using this model, we can integrate all those environmental factors to do the prediction of the fraction of the associated mineral associated organic carbon. So we can deliver a 1 kilometer to 1 kilometer spatial distribution of this FMOC data. Then we can using this data to initialize the basic partitioning fraction of the organic matter in the CM. So then let's see how to incorporate that into the model. We know that the decay rate of each soil carbon pool in the CM that can using this general equation to describe, but they have not incorporated the association process into. So we are now introduce a function of the FMAOC using basically the external decay equation from a very classical paper in 1995. Then we're using the 14-cell neon set across 18 equal regions, trying to calibrate all the parameters related to these functions. To make this more efficient, we're using this AI surrogate model to basically to train the parameters. So the figure on the right does showing that our AI surrogate model can well capture mimic what the CM is doing. And so here the distribution showing we do the 1,000 iteration of the random basic sampling of the training and testing and validation data, and the overall model show very stable and high R square across all these different iterations. And then we using the basically the LM metrics that using for all the land surface model to show the model performance to evaluate the this new version of the CM model across all those 47 neon sites. So the left here is the control model, the right here is the CM model with this mineral association protection mechanism. And each row here relate to the each neon equal regions. So we can see each column here relate to the R square. So if it's higher, means model overall perform better. MSE, we're also using the KGE. If the KGE higher, also showing model is better. And we're also using the LM define this seasonality and also intra-annual variability metrics to evaluate the model. So overall, we can see that by representing this mineral production process, CM can better capture the soil respiration from those 18 neon sites. Another thing that, as we mentioned, is this resource allocation strategy of the microbial community. So biologists already introduced a lot of multi-omics data trying to understand those microbial function in the soil, but they are still very complicated to be utilized in the Earth system model. So to answer this question, so we actually define a term, follow the concept of the plant functional type that is called the enzyme functional class. So we defined it as a group of the gene encoded enzymes that can catalyze the decomposition and mineralization of a similar group of soil substrate. So we synthesize basically all the published omics data that can inform what gene in the soil, what is their function in the soil, and then we corresponding those genes with the corresponding environmental data together train this machine learning pipeline. So because the genomic omics data is very limited, so with this machine learning model, we're able to further generate and understand how the environmental factor will regulate the relative abundance of those functions related to the carbon, nitrogen, and phosphorus decomposition. So the figure on the right, that is also the prediction result by this model, and that is showing the spatial distribution of each of these enzyme functions across the whole corners, how that is distributed. So for example, EFC carbohydrate, that is means those enzyme functions in the soil, how relate to the carbohydrate abundant organic matter decomposition, how they are distributed. So with this model, we also further train a model trying to understand that how the historical soil hydrothermal condition and also the current soil hydrothermal condition will further regulate the relative abundance of those 8 EFC we defined. So here we're using the climate data trying to define those soil drying properties and and also soil temperature properties like the soil drying properties over the past week and also past month and past year compared with the sampling date of this basically the soil sample. Then we synthesize this all the data, also train this model, and this model allow us to better understand those allocation strategy of the microbial community. For example, here we found is that it's true that across all the basic data we found across the corners, if the soil moisture is lower, that basically can decrease the abundance of those soil enzyme function related to the lignin decomposition and also the organic, basically the phosphorus and also the nitrogen mineralization process. And if this is also will be more obviously in those dry lichen soil. So here SMF means that in the history, this soil has very low soil moisture flow, and SMDD, this means that the soil drying duration, if it's larger, that also will further trigger this process. So this actually justifies the hypothesis we provided at the beginning. But if there's also the nutrient limitation here, that actually will mitigate this process. And we also can find that how the thermal legacy will also further drive the relative abundance of those different EFC. Actually, the microbial community can well adapt to the soil condition where has a larger temperature variability, or in the history is experiencing very extreme warming conditions. So using this model, basically that can also inform us what the environmental factor, important environmental factor relative to the abundance of each of those EFC, then we can using this to replace the original temperature function, moisture function in the CM model, because now those environmental factors already be incorporated into this AI model, so they inform the enzyme function. Enzyme function can link with the decomposition rate. So in the same way here, we actually now can replace the whole environmental factor in the CM. So here we're using the two forest set as an example to showing how this version of the model will perform. So these two algorithm forest sections, they are the location one is in the Yellowstone, another in the California. They have a very accurate larger temperature variability and also the basic soil moisture variability. And the result here is also showing those element metrics. We can see that when we consider how this optimize the allocation strategy of the microbial community for those EFC related to the lignin decomposition, model can better capture the soil respiration compared with before. A more important thing and useful is that our model framework allow us to interpret how the past and the current soil moisture temperature metrics, they can basically how soil respiration will respond to there. Here we're using this probability density function to inform that how the soil respiration will respond to the temperature and moisture metrics. We can also see that when this microbial community allocation strategy was incorporated, model improvement is also better improved. So this is a take-home message. And I think if time, I will stop here and give the time for the questions. Thanks.
Because we are behind for a couple of minutes, so let's move on.
Hi everyone, I'm East University. Today I'll be talking about how we use physics-informed neural network to improve the predictions for soil CO2 flux in subalpine forest.
Excuse me, can you turn on the microphone back?
Yes, sorry. The work is about to use physics-informed neural network to improve the predictions for soil CO2 flux in subalpine forest. And the work is as part of the SNOWDY project funded by DOE. And the central question for the project is how does cold season climate affect soil CO2 flux and its plant and microbial sources? To answer that question, we use long-term soil measurements, and we also included some new measurements like soil CO2 flux measured in winter, which is also important components, and the carbon safe for partitioning its sources, and Q-safe quantitative stable isotope probing for microbial growth. And those data sets are combined with machine learning and process-based tools to answer the question. This is a collaborative work across NAU, NCAR, and Lawrence Berkeley Lab. And the team spans in expertise in radiocarbon, microbial ecology, soil biogeochemistry, forest physiology, process-based models, and machine learning. The range of expertise allows us to tackle one of the most challenging components of carbon cycle, soil CO2 flux. It's a large flux in carbon cycle second to photosynthesis, but it has been difficult to model as it's a combination of two biological sources, microbial decomposition and root respiration, which are driven by different environmental and biological factors. And it's difficult to tease them apart. And our measurements took place in Snodgrass Mountain in East River Valley in Colorado at 2,880 in elevation. We work on dominant forest types, aspen and mixed conifer, spruce and fir stands. From 2014 to 2024, the study size has experienced variable snow and rain inputs, increasing soil and air temperature, decreasing soil moisture, and decreasing soil CO2 flux, with surface soils being responsible for the declining trends. Therefore, the motivation is to improve to guide more accurate and ecologically realistic modeling of soil CO2 flux and its microbial and root contributions. A little bit background for the goal of classic machine learning. It is to minimize the loss. Usually it's the mean squared error between observations and the predictions. This is good for fit, but it says nothing about if the learned response to drivers are biologically reasonable. So that means traditional machine learning methods may overfit to data, lead to biological implausibility. And for our case, for soil CO2 flux, because both temperature and moisture vary seasonally, at the same time, carbon supply is changing. So it happens that the effects from moisture and the carbon may be incorrectly attributed to temperature effects. And the PIN physics-informed neural network can help with that. The central idea for PIN is to modify the data loss with a process-based penalty. We still have the traditional data fade term, but we add a second penalty term to nudge the model towards obeying a physical law. So that means we can add our domain knowledge directly during the training process. And in the figure, it says PDE loss, but it does not have to be a partial derivative equation. It's actually more feasible with the modern tool of neural network. You can also add other constraints. And for my study, I added Q10 as a constraint. Q10 qualifies how biological reaction rates change with a 10-degree Celsius increase in temperature. And the value of 2 is often used in process-based model to represent the temperature response of a plant or ecosystem. And the model took daily soil CO2 efflux, soil temperature, volumetric water content, snow and precipitation and the forest stand type as input. And then we trained 2 models with same architecture, but we add additional Q10 term for PIN. Then we tested the weight for the Q10 term. Here we call the weight lambda. And before the end, we computed the local Q10 for each sample. Now we are looking at the model performance. Here the green dashed lines are for the model performance for classic neural network, and each point represents Q10 constrained with different lambda. For the choice of smaller lambda values, let's say 1 and 5, they are the blue dots in the figure. Q10 constraint PIN outperforms classic neural network. But as lambda increase, the model performance began to decrease. We understand that's because Q10 constraints are keeping the model from overfitting to data. So we understand it's a good thing, not a bad thing. Now we are looking at the distributions of Q10 from different models. Again, the green line is for classic neural network. And we will see highly scattered Q10 values with high variability. And the PIN narrows Q10 estimates to a biologically plausible band. As lambda increase, the Q10 values become narrower and are put closer to the target value of 2. For example, if we look at the line for lambda of 100, which is pretty high value, and the Q10 is basically centered around 2. Then we plot Q10 against soil CO2 flux. And the figure is colored by volumetric water content. We will see a lot of implausible outliers, especially at the high end. But Q10 constraint PIN stabilize the behavior. With the choice of lambda of 1, we already see fewer outliers. And lambda of 5 seems offer good trade-off between stability and allowing natural availability. Then what if, again, we apply a high value of lambda, let's say 100, the values are too tightly constrained around 2. Now we are looking at the time series for soil CO2 flux and Q10 for conifer only. Just to recap the point I had before, Q10 constraint pin with lambda of 5 has slightly higher RMSE and R squared than classic neural network. Surprisingly or not surprisingly, it produces the signal patterns almost identical to classic neural network. And they smooth out some abrupt jumps that are visible in the measurements, but may not be realistic. And for the bottom panel, we are looking at the time series for Q10. We will see Q10 constraint pin has more realistic seasonal variation in Q10. Both the extreme high and the extreme low values are immediately eliminated. They are likely coming from like moisture effects or carbon effects being inaccurately attributed to temperature effects. And another experiment I did is to use the 1 year out to test the model generalization. And the purpose is to look at if our model make good predictions for untypical years. And the first panel here I'm showing on the right side is for 2022, which is a normal year in terms of winter snow and the precipitation inputs. And the green arrow shows decreased. I'm plotting the observations on x-axis, and the y-axis is the change in prediction from classic neural network to Q10 constrained neural network. And the blue up arrows, they show an increase, and the red show decrease. So we will see a lot of changed values in the predictions, but the overall RMSE was similar for classic model and Q10 constraint pin. Then how about 2 other years, and 2015, which was with most extreme rain and medium snow, and 2020, where the study sites experienced low snow and rain input and a dry summer. Actually, our Q10 constraint model works better here. However, for another year, 2019, where we'll say we saw high snow and the dry summer for that year, the Q10 constraint model, we didn't see a decrease in RMSE for that year. But back to the point I made before, we care about not only the predictive accuracy, but also the ecological realism. So here are just some preliminary results. I will check out the Q10 behavior or how it's in relation to CO2 flux or soil temperature, volumetric water content data. So for future efforts, the goal is to predict not only soil CO2 flux, but also microbial decomposition and the root respiration. Within SNOWDY project, PhD student Austin Simon Petrie has led the measurements using 14C partitioning to understand the fractional contribution of the heterotrophic and autotrophic respiration. This is a valuable measurement which requires a lot of lab and field work, but it's sparse data. Throughout a water year, we had about 7 samples in the yellow box. This is partly because of logistic reasons, and also partly because we have to leave the soil traps for a few weeks to allow the CO2 to circulate in the soil trap before lab analysis. So to make best use of the sparse measurements and also model simulations, we are thinking about the way to combine them into a neural network framework. We plan to use COM and mimic simulations under different scenarios, let's say RCP scenarios or different environmental conditions to pre-train the model, and then use isotope partitioned measurements to fine-tuning the model. On top of that, we will add mass balance and the different temperature sensitivity and substrate supply to as physical constraints. So to wrap up, classic neural network, which is pure data-driven but may misattribute effects from different drivers, and the pin gets temperature sensitivity towards biologically realistic values without sacrificing accuracy. Do I have time for questions? Thank you.
So I think that one question.
Yeah, thanks for the nice talk. I'm wondering if you're showing that the neural net that doesn't have the Q10 constraint in it is able to capture the more anomalous years better than the one that does have Q10 constraint. Did I interpret that to mean that maybe Q10 shouldn't be constant, or am I reading too much into that?
I think our constraint is to Q10 is constraint, but neural net being happy to approximate it in different ways. So the choice of different lambda, I'm still thinking about should I have a tempo lambda or just keep it as a constant weight to force the model. So that's something I'll be interested to test in the future. Thank you.
Great, thanks. I'm excited to actually give a science talk at this meeting. It's something I feel like I haven't done for a while. And this is work that's very much inspired by, one of my other jobs is I work for work with the Niwot Ridge LTER site, which is just up the road outside Netherlands, as well as on the project at Snodgrass that Yuji was just introducing. And then also the Ember project, which is based out of Idaho. And so all three of these kind of ecologically focused groups are really interested in starting to think more about winter. And so that's what I want to talk about now, especially in a year that we don't have a winter. So at a lot of ecological field sites, this is kind of like many people's conceptual model of what the site looks like. And that's true for about 3 months out of the year at Niwot at least. And so actually a lot of the year it's snow covered, maybe this year accepted. But snow is kind of a dominant feature of many of these Western landscapes, especially at high elevation. So some work at Niwot in the 90s kind of came up with this conceptual figure. This is from a paper that Steve Schmidt led with Dan Lipson, looking at the kind of this phenology of microbial biomass, which actually peaks at its highest under the snowpack. So in kind of late winter, early spring, microbial biomass peaks, and then it crashes along with snow melts. And during that crash there's this huge flush of available nitrogen, which is shown by the dotted line, I guess. And so microbial biomass peaks under the snow, then it crashes, all this nitrogen is released. And I think that's probably the kind of idea is that that's an important time when plants are greening up and nitrogen availability is really important. And so this kind of temporal disconnect between nitrogen availability and plant nitrogen demand is something that's probably characteristic of these systems. I also want to emphasize that this conceptual figure is based on very, very sparse data. And so the project that Yuji was talking about and the work that Austin's done is also kind of filling in some of these gaps with more sparse data. And also at the East River site, the DOE group and Pat Sorensen and others have done some really interesting wintertime work. And that's kind of what's inspiring how I'm thinking here. So I'm going to move down slope and I guess further west from this conceptual model at Niwot to Snodgrass. This is a picture of the East River Valley. And it's really a joy to get to work in a place like this. I haven't got to go nearly enough. But again, this is a project that's being led by Mariah Carbone, and she's been working there for a decade. And then Austin and Jenna are two of the graduate students that are also contributing to the project. Okay, so kind of similar to Niwot, many of us maybe have gone to to Crested Butte or the Gothic area for the mountain biking, and like zipping through the aspens is just magical. But it turns out that, in most years that's snow covered. So these are photographs from the phenocams that are up at the site. So even, late into May, the aspens are still snow covered, and as early as in November, they can be snow covered again. And so what I kind of wanted to start with was just testing, there's no flux towers here. And so I wanted to try to get a version of CLM running for point simulations. Here I'm using NLDAS data, which I had zero experience with. And anyone who's done point simulations kind of knows it's a bit of a bear to even just test the data atmospheres that we're running the model with for adequacy. And so I tried a couple runs with CLM6, both with BGC and SP, just to make sure that I could kind of capture the phenology, like the seasonal timing of snow. These observations are from the Snowtail site, and it's over a water year. So for historical reasons, the water year around Gothic, they think of as starting in September. So the snowpack kind of sets up and melts in the model, similar to what's happening at the Snowtail site that's on at a nearby over at Mount Crested Butte. And then soil temperatures also kind of roughly match some of the observations that Mariah and Austin have taken, where soil temperatures are actually relatively warm, and then importantly, don't freeze all the way in the summer. So that snowpack's really important to provide an insulating barrier. And so without that kind of biophysical model adequacy, there's no way I could start thinking about the microbial things that might be happening under the soil. So this is just, a sniff test that we're able to kind of capture the biophysics correctly. I also am doing this run with mimics in CLM, so it's exciting to, a decade later, Katie nicely nudged me last year saying, hey, it's been a while since you've been working with this model. Why don't we use it in CLM? So this is now running in CLM, and just briefly, mimics thinks about kind of, I guess, three important characteristics. So one is substrate quality. So there's high quality and low quality substrates that microbes eat. The original conceptualization of mimics had these two microbial functional groups, and this is my attempt to be as interesting as Fates, but below ground. And so coexistence of microbial functional groups is similarly challenging, like it is in Fates. And so what I originally started with this was this concept of fast and slow microbial groups. And so the fast microbes tend to eat the candy, the slow microbes tend to eat the carrots. And then when they turn over, the carbon is stabilized through different mechanisms. And so there's a mineral associated organic matter, like pool that's physiochemically protected. There's a more kind of recalcitrant pool that's like a particulate organic matter fraction, and then an available pool. So these are the assumptions that we put into mimics, and we were explicit that we wanted this model to be kind of generalizable enough that we could run it globally. And what I want to present here is kind of an adaptation of this fast and slow group into thinking about a summertime community and a wintertime community. So these might be, the Texans that come up and enjoy Crested Butte in the summer, and then this is, the ski bums that hang out in the winter. But below ground. And again, trying to get coexistence of these communities is one of the challenges that we had. Okay, so going back, I only have one figure, but I think it's going to unpack in very complicated ways. So kind of brace yourself. So again, this is on the x-axis going through time, on the y-axis over an average snow year. So these simulations, I think I ran for a dozen or so years, kind of in the 2010s. And so from September through September, snow depth sort of sets up in reasonable ways. Soil temperature looks relatively okay. So importantly, observationally, it takes about 20 centimeters of snow to physically separate the atmospheric state from what the soil conditions are like. And so you kind of see that on average, once the model gets 20 centimeters of snow, soil temperature kind of stabilizes. And then importantly, soil moisture, the idea of liquid water is really important for controlling what happens underneath the snow. And so, the soil moisture or liquid water availability is going to be an important part of the story. So soils can freeze, especially in December. And what really depends is the interannual variability of when that snowpack sets up. So that's one of the kind of important things that I want to hold on to. And then similarly, the timing of snowmelt really matters in terms of thinking about when soils warm up again in the spring. Okay, so here is same 3 plots: average snow depth, average soil temperature, and average soil moisture. And then this is what the winter microbes are doing. So they're kind of persisting through most of the winter. They sort of peak close to when the snow is melting, and then crash in the summer, and then net nitrogen mineralization sort of corresponds with that. So you get relatively low rates of nitrogen mineralization until that kind of flush of snowmelt in winter microbial communities. But they're not crashing fast enough in kind of an average sense. And so I needed to kind of dig in a little bit more to see what was happening. So to do that, I wanted to look at, I kind of picked canonical years. So 2012 was one that had kind of above average December snow, but then an early melt. So this would have been, a great time to go skiing in Crested Butte in December, but not so much for spring break. So the snowpack kind of reaches that 20 centimeter threshold early in the year. And as a result, the soils don't freeze at all. So you don't see this dip below freezing, which was kind of one of the things that we were looking for. And also we had relatively high, because the soils didn't freeze, there's a liquid water availability. Part of that was because of the antecedent conditions. So there was a good summer monsoon in the preceding summer. So soils went into winter relatively wet, and they stayed relatively wet throughout the winter months. Then once the snowpack melted, soils froze, and that liquid water kind of went away. So there's this kind of really quick change with snowmelt. And here the winter microbes actually kind of behaved. And so they peak, they keep growing throughout the winter. And then as soon as the snowmelt goes away and the soils actually get kind of cold in the spring, that microbial population starts to crash. And then the summer microbial population starts to pick up, although maybe not as rapidly as I would have wanted. And then the interesting part here is that the nitrogen mineralization is actually quite a bit higher than average. The black line is the kind of average climatology. And so when you have these winter microbes setting up under the snowpack, the nitrogen mineralization is sort of doing what I would have expected. I don't want to pretend like it's all rosy though. So this is water year 2020. We had a below average December, but then otherwise a relatively average snow year. As you might expect with a low snowpack in the winter, or early in the winter, soils froze. And as a result, they froze early, and then that liquid water was really gone. And so they froze, but then it became ice. And as a result, the winter microbes totally collapsed. They just didn't function that year. And as a result, there's really low soil nitrogen mineralization rates. So you can kind of think of this, even though it was an average snow year, because the preceding conditions, because that snowpack was late to set up, it prevented these kind of winter dynamics from happening. And so as we move forward into winters that are like this, when there's really, really low snowpacks, I think the kind of the idea would be that you'd have more, or the model hypothesis would be that you'd have more situations like this with really low nitrogen mineralization rates. What that means for above ground is a totally different story. I think we don't have a very good handle on timing of plant uptake of nitrogen and when that happens. It's very demand based in CLM now. And so there's a whole bunch of stuff to do. And so Jenna measured QSIP, which is magic, and she did magic under the snow. I'm not going to go into that, but it kind of gives us some ways to quantify growth rates and growth efficiencies. There's a bunch of assumptions I made here about stoichiometry and substrate preferences of winter and summer microbial communities that I just totally made up. So it'd be nice to compare those with data. And then another sort of interesting part of this is what's actually causing that crash of wintertime communities. There's some literature out there suggesting that turnover mortality is actually a top-down control. And so it's actually predation by phages or nematodes, things that eat microbes that when soils are frozen, the predators can't really do much. But then as soon as they warm up a little bit, that's what kicks them off. I think there's some interesting links with kind of top-down controls that the ocean biogeochemistry thinks about that would be fun to think about. And then stress tolerance and the environmental triggers that I'm using to create these summer and winter microbial communities really would be helpful to think, kind of a nod to the ecological community. And I don't do that much work anymore, so I could use some help there. But then the other thing that I think was really interesting here is the importance of antecedent conditions. And so the summer monsoon is really important in kind of setting up what the soil moisture state is for the winter. And that fall precipitation really matters, whether it's coming as snow or increasingly rain. And then finally, the wintertime snowpack and the timing of melt is important, not only for plant phenology, but it's also really important probably for microbial phenology. That's it.
Question.
Like you sort of got it. What does it all mean?
Yeah.
I still feel like that's doing it.
Yeah, I mean, I think the biggest thing is
models seems to be doing
it does interesting stuff.
Plausible things that you could imagine.
Right. It doesn't actually, the other thing I show was that it's really driven by the biogeophysics. And so even though I have these winter and summertime communities, it's not that different from CLM century, which is a little disappointing because it's totally driven by, I know it's like, oh, I wanted the microphone there. But it's really driven by biogeophysics. So it's like the timing of temperature and moisture scale, temperature and moisture scale is really there. It's driving the show.
Do you have very different sensitivities to these moisture scalars of your communities, or can you?
Not right now, but you could. Yeah, you could put that in. Be sort of interesting. Yeah, I guess, similar to fates, it's like once you add it in, like there's a bunch of hypotheses you can start investigating.
Oh no.
It's not big.
Just that one.
All right. Thanks. I am going to be presenting on this observationally constrained PPE that we've been constructing for several years now. I've just finally got these simulations finished last week, so it's very early, and that's why I'm more exploring carbon cycle dynamics still. I want to stress that this has been a huge community effort, and there's been a ton of people who have contributed to developing these PPEs, and it's been supported by the LEAP NSF Science and Technology Center. So we've seen a lot of examples of perturbed parameter ensembles over the last couple of days. They're really valuable for exploring models in new ways, understanding parameter sensitivity. We have used them to calibrate CLM6, and there's a bunch of other calibration studies we've seen. And I think we're just really starting to learn how to use them for more science type questions. How can we set up different types of hypotheses with these PPEs to test scientific hypotheses? So this is all really exciting, but what I've been trying to work towards for many years now is I'd really like to use these PPEs to quantify and constrain parametric uncertainty in our projections. And we've always been focused on this land carbon sink. So thinking back to Abby's talk at the beginning of this meeting, she showed how much uncertainty there is in the land carbon uptake. This figure shows the spread in land carbon uptake across CMIP6 models. And then this is from Daniel's study that shows the unconstrained parametric uncertainty in the land carbon sink just from CLM. But this is somewhat of a, it's not quite a fair representation of the parametric uncertainty because it's unconstrained. And we have this hypothesis that if the model represents historical observations well, then it should be a better tool for asking questions about projected changes. So we want to actually construct an observationally constrained perturbed parameter ensemble in order to better quantify this parametric uncertainty. Okay, so to construct an observationally constrained PPE, the first thing you need are observations. And so we started with leaf area index, GPP, vegetation carbon, and latent heat. I'm also using soil organic matter carbon as well. And we've talked about this a lot over the course of the meeting. There's a lot of different observational products out there, and we're trying our best to kind of draw on them. So we just pulled everything that we could from ILAM. And we're doing this at the biome scale. So I've constructed these 3 biomes that are based on coexistence of PFTs. And then I'm just showing the observational products for one biome, the tropical rainforest. And I'm just want to highlight that there's a lot of spread in these observational products, right? And rather than choosing one and assuming it's the best, we kind of set the observational uncertainty as the spread across these products, plus another plus or minus 10%. It's a little crude, but that's what we went with. And this is probably an underestimation, right? We saw earlier that the GPP estimates could be, much higher than the products that are on ILAM. So, this is, I'm trying to set this observational uncertainty as a conservative estimate, but it's still probably too narrow. Okay. So I want to also just highlight that there's this there's the center of the observational uncertainty, the black dashed line, and I'll come back to that in a minute. Okay, so you've heard me talk about history matching a lot. I'm using it as a tool to construct a perturbed parameter ensemble. Rather than just running all my simulation compute budget and doing a Latin hypercube sample, I really want to concentrate the ensemble members towards the observational uncertainty. And that way I'm not still sampling up here in this unrealistic range for a lot of the ensemble members. So the way that we do this is start by generating a Latin hypercube sample, but a small one, a 200 member ensemble for 56 parameters. Train an emulator on that PPE. Use the emulator to sample the parameter space really densely, like billions of samples. And then I can rule out any parameter combinations that aren't in agreement with the observational uncertainty. That constrains my parameter posteriors. I then resample from those and run another 200 member ensemble. And I cycle through this for these waves of history matching. And gradually that allows me to concentrate the members of my PPE in the kind of good region of parameter space. Okay, so this is my tool. History matching is just a tool for constructing a PPE. What I want to do next is develop this observationally constrained sort of calibrated PPE. And so a typical tool that is used to characterize that parametric uncertainty is Bayesian inference. And it, by definition, assigns the highest probability to the mean of that observational product, but then has less likelihood towards the spread of the observational uncertainty. And I've been very resistant to MCMC methods over the years because I just haven't had success in this, for land modeling specifically, because we're working in this really high dimensional parameter space and it's really multimodal. And that's just an application where MCMC typically fails. So I've been resistant to it, but I recently came across this Hamiltonian Monte Carlo method that it leverages the fact that the emulators are differentiable. So it allows us to kind of know what this gradient looks like. The Hamiltonian kind of knows where what that shading looks like, where the holes are. This is kind of a simple example, but because the emulator is differentiable, we can make these really informed big steps in MCMC rather than just kind of the typical guess and check of MCMC. So the fact that the emulators are differentiable enables us to do this Hamiltonian method, and that scales really well to a high dimensional multimodal problem. And I've been really pleasantly surprised with how well it works and also how fast it is. I can run a lot of 30 chains with a bunch of steps on a GPU in a tropical rainforest. And then this is that same figure from the history matching again, and it's shown, I'm trying to highlight that the Hamiltonian Monte Carlo ensemble is fairly concentrated towards that center of the observational uncertainty, and it falls within this kind of target. So I sampled from these posteriors, ran 200 ensemble members, ran CLM for 200 new ensemble members, and that's the purple ones I'm showing here. So this is what I'm calling my observationally constrained perturbed parameter ensemble. Now we can look at how that, how our projections in the land carbon sink look in this constrained space. So I'll show this figure in several different ways. So just to orient you, this is the cumulative land carbon sink through time from 1850 to 2100. And my 1,000 member history matching PPE is shown in gray. And this histogram is just the kind of end of century cumulative NBP. And then the observationally constrained ensemble is fairly tightly constrained during this, the early 2000s, which is when I'm introducing the observational constraints. So that's good. We've ruled out a lot of the parameter space that results in really high carbon stocks, high carbon density in the tropics and boreal forest. And then we've also kind of ruled out some of these higher carbon uptake ensemble members. But there's still, and so I think this is good. We're showing that observational constraints can constrain our projections, but this is still a lot of spread. Like this is order 300 petagrams of carbon, which is still a lot. And so I'm trying to start to analyze this ensemble and think about what is driving that remaining uncertainty and whether we can introduce new observational constraints, as we've been talking about, to further constrain this uncertainty. So I'm just starting to play with this, but here are two ensemble members that have a fairly strong or weak CO2 fertilization effect during the historical period. It's not there's the climate signals in there too. It's not a perfect trendy simulation, but it's approximation. So CO2 fertilization seems like it's a strong driver of this uncertainty, unsurprisingly. And that's true for looking across all the ensemble members. There does seem to be a relationship between the strength of that CO2 fertilization trend and the carbon sink. So that's good. That means that if we can bring in observations of how strong we think that CO2 fertilization effect might be, then we can maybe further constrain these projections. And thinking back to Abby's plots that she showed where these zonal NBP across models, I'd be interested to see how these different ensemble members look in comparison to the cross-model distributions. See how different the spatial, where we're putting this carbon looks across the PPE members. And we can do the same thing for several other variables or processes that we observe. So here I'm showing a weak trend in biomass during the historical period versus a strong trend in biomass. And there are maybe some estimates that we could draw on to constrain that trend. And then water use efficiency, strong and weak, kind of mid ensemble, I don't know. There's probably more quantitative ways we want to analyze this. I'm just kind of pulling out some initial observations I've had a week. So my takeaways so far are that our historical mean state constraints, I'm only constraining on the mean state of LAI, GPP, veg carbon, and latent heat. They do seem to be constraining our projections in the carbon sink. But it's likely that we need to think about trends or variability or different measures of observational constraints to further constrain that spread. And then it seems like the CO2 fertilization effect and the trend in biomass explain most of the remaining spread in that carbon sink. That's just preliminary though. And then I want to highlight that our assumptions about observational uncertainty really influence this assessment of parametric uncertainty, right? The spread is really conditioned on which observations I used and whether I set the observational mean to be more accurate than the spread across observations. So, and since I think I have a little bit of extra time, if I don't assume that the mean is of the observations is more likely than anywhere within that observational uncertainty, then I get this blue ensemble, which has a pretty wide, a little bit wider spread. The Hamiltonian Monte Carlo assumes that the mean is more likely, and so that's why we get this difference. So back to my summary here. I think there's a lot of opportunities for how we could start to use an observationally constrained PPE, and I'm just looking at the carbon cycle, but there's all sorts of things that people might want to look at. So I want to make this available to the community, and I think it could be a basis for selecting alternate versions of CLM, as Dave mentioned yesterday. And then we want to explore some of these new parameterizations in the emissions-driven coupled model eventually. So that's where we're going with this. Thanks.
All right, so now we have a few minutes. I think we have until 4:30 on our schedule. So questions for Linnea and questions for all of our speakers from this session.
Yeah, very interesting work. I just wonder for your whether the unconstrained versus constrained, you have like big spread of different ensembles. If you put that spread in the context of this CMIP6 ensemble spread, which one is bigger? So I guess my question is like, after you using the observation to constrain the spread, is that how much better it is for the current CMIP intermodel spread?
Yeah, I see what you mean. So this is still on the order of 800 petagrams of carbon, I guess maybe in 100 years. So, and my spread's maybe 300 petagrams of carbon. So it's less than the spread across CMIP models.
Apples to oranges, right?
Yeah.
Yeah. I was going to say at the similar CO2 flat time MIP would say it's more like 150 across the models. So yours is bigger.
Mine is bigger.
Yeah. So yeah, I guess like how your approach can better really, this is the ultimate goal, right? To reduce uncertainty here. Yeah. So I guess that's the big question.
And I guess, yes, we want to reduce uncertainty, but we also want to just uncover and highlight where the uncertainties are. Yeah.
That's right. Yeah, on your last slide, your last bullet point, you have this, emissions shooting, right? I guess I'm a little skeptical, right? Because it seems like what you're doing is very conditional on the actual history, the climate being what it is. And so I wonder if the better application for this is like a WEMIP thing than an emissions-driven scenario. Because once you move from offline to coupled, how can you argue that it's history matched anymore? Because you've just changed the history, unless you recalibrate everything.
Well, what about for the future?
Yeah, I'm not.
Yeah.
I'm not really the person to answer. Sorry. I don't know enough about WEMIP. I've been tuning the CLM6 and really changing things what I thought were kind of dramatic, and the atmosphere hasn't even noticed. So I know it's not emissions driven, but
I guess I just mean given that the climate's totally different, unless you're doing all the history matching with the coupler forcing, right? And that's not what you're doing, right?
No, it's not what we're doing. So I guess maybe a different way of phrasing it is could we test hypotheses in the emissions-driven mode? What if we had a strong or weak CO2 fertilization effect? We can design the land model to sample those two hypotheses.
Right.
So I guess it's not, I wouldn't say it's history matched, but it's more hypothesis testing. Is that fair? Maybe.
But I would be thrilled to do this with WEMIP. Pick your high.
Can you tell us what WEMIP is?
Sorry, WEMIP is the Warming-Induced Emissions Model Intercomparison Project, which is a blessed MIP now. As of last week, as far as I know.
But what does that?
But it's land only, so it's land only, trendy,
future,
but into the future.
Cross scenarios.
How do they make up the temperature?
Using UPSM and thinner.
Okay, so they just made up a future temperature and then they're doing it for us with all the same temperature.
That's not too much different than that, right? This is just one.
Exactly. Yeah. No, exactly. Yeah, but it's just but then it's across a range of ensembles. And do the sort of direct comparison against other models, against this kind of this question of like, the Aurora et al., C4 map, there's gonna be a bunch of models that are doing WeMap. And so you'll be doing like, you could do the direct comparison.
Okay.
And that's right. We put that into the.
Yeah.
I still feel like a couple emissions driven will be an interesting result.
Maybe it's just not history knowledge. Which it's not observationally constrained.
No, but what I think is interesting is that you would get feedbacks in the future, maybe not so many in the present day, but if you have a model that's got really high land uptake versus really low land uptake, it's going to either propagate differently into land and ocean sinks or change the amount of CO2 in the atmosphere, which will feedback on climate. So the interesting part is not how you figured out which ensemble members to select, but how they led to something different in the future. From the emissions driven side. It's very interesting to pick.
Can you go back to your latitudinal distribution? I couldn't tell if that was just 2 ensemble members that are on there.
Oh yeah, sorry.
No, it is. Okay.
This is CLN 5 in gray. And this is the high CO2 fertilization member in low. I have a scarier plot. I wasn't going to show
the cumulative.
This is all the ensemble members.
Oh yeah.
Easy. I haven't looked at this like why, but these are projected changes in veg carbon, changes in GVP, and then QMUT. I don't know what to make of this. I made it last night.
Well, yes, thinking about the WeMap example, like comparing for whatever is a good comparison, but like looking at the spread that you're getting in terms of the latitudinal distribution of sources and sinks and what those look like across this parameter ensemble, I think would be really interesting.
Yeah, my guess is we probably don't have, there's an argument that it should be shifted more toward the boreal forests. I bet we're not quite sampling that spread well.
Yeah. But you do have ensemble members that are losing lots of
your tropics look vulnerable.
Looking vulnerable.
I mean, like 3 ensemble members.
Well, but there's a bunch that are lower, right in the middle, right? Yeah. Even if they're not, maybe there's only a few that go negative, but there's a bunch that are lower than others. Yeah.
And do you not have, is there a permafrost curve in feedback at all at these? Or is it?
I guess I'm not sure, Dave. I got confused about what that is. So.
Well, in our discussion the other day, you were just trying to select for either a strong or a weak change in the active layer thickness, right?
Yeah.
And I was just saying that there's the additional whether or not the carbon responds to thawing, basically, strongly or weakly. So we have to determine how we pick those out. As I was saying, it should be another axis, I think.
Yeah, any guidance on things people want to pick out of this to create multiple versions of CLM would be great to get input from the community. Yeah, Evan.
In the traits, were you seeing any patterns in the kinds of traits that were getting constrained more than others, or were there allometry and allocation traits were unconstrained, or hydraulic traits were more constrained, or any interesting thoughts there?
Yeah, I haven't looked at it enough to say anything. I'd love to look at that more. The biomes where I'm really pushing, the tropical forest carbon was really high and I had to really push it down. And that was doing it through both high mortality and high water stress, which I think is what's giving me the vulnerability there. And then the more allocation or Lucian and top, they kind of trade off with each other. So they're really unconstrained. I'd be interested if you wanted to look at those. Let me know what you see. I don't know.
Yeah, I'm just thinking just because Ben and I looked at somebody came at stuff where it was are we really stressing out the plants in the tropics to get lower biomass there? Is that
yes?
I mean, is that a legit thing?
Yeah, just because we can doesn't mean we should.
Yeah, are the tropical trees actually hydraulically stressed that much? I mean,
and
matter.
it's so sensitive to the height of the trees, this parameterization that I'm not sure. There's probably lots of things you could look at and like, oh, I don't know.
I'd be curious to see the comparison between the one where you assumed the mean was better than just taking, like, does it fall in your window? Because I just feel like the uncertainty ranges on a lot of these observations are big, and I don't know that we were informed that the mean is a better estimate.
I completely agree. Also, why I've been really resistant to these like calibration methods, but you can do it from the statisticians if you don't do a posterior. Yeah, Peter.
I'm wondering, like, when there's climate drivers for like sensitivity, whether you can use like maybe space instead of like, parameter space, geographic space. So you find areas and saying, well, what happens current day in terms of the stresses for water or for temperature or those sort of things. So instead of like just trying to look at it like in situ and see how it moves up and down in the same climate space. So well, what happens in a different climate space in the current day distributions of vegetation?
Yeah, that'd be an interesting axis to analyze this on. It's a good idea.
Doesn't work in the tropics though.
Right. But we can still get gradients, still get ecotones and everything else. So like you'd be able to work across a climate gradient.
You're just missing wherever it goes in the future. It doesn't exist now.
Right, but I'm more thinking about this period that we're looking at here.
Yeah, during the historical.
Yeah. It doesn't tell you the CO2 response, obviously. But if you care about some of the climate drivers, yeah.
Is this Hamilton Monte Carlo thing like purely to like satisfy the statisticians or
Specific statisticians or just general?
Name names. No, you're being recorded.
No, I do think it's like, so the history matching is random sampling. And I have these 13 biomes and 4 variables, and it's really hard to get a random selection of ones that fall into all of those 36, bullseye for all of those 36 targets. And so that's actually where the MCMC comes in, and it helps search more efficiently, and I get a much higher ratio. So of my history matching, there's 1,000 of them, only 210 meet all my criteria. Of the HMC, it's only 200, and more than 50% of those meet all my criteria. So that's another motivation for it.
For the HMC, could you inflate the uncertainty? Like increase your.
But it still aims for the middle.
It still aims for the middle.
Yeah. Okay.
You can't give it a probability distribution of the range.
or could you just run a bunch of them like with the corners of the
Oh
box?
yeah, you could. Oh, you could sample
Instead of the
the
middle of the
mean
box.
and do that 100.
That's actually kind of what we did with CLM6. I did gradient descent, but started in a bunch of different places, and then gradient descent without, and tries to stay close to default. So maybe you could set targets in the corners and just do a simple gradient descent to the corners. That might work. I see an email in my future.
It's all on GPUs though. It's like a day on GPUs, right?
Yeah. Oh, it's still to run CLM, but it's really fast.
All right, well, we're out of time. I think there's more to talk about. I think we should have